Mars, a red planet, a neighbor to Earth and one of the most fascinating destinations in our solar system. For centuries, humans have gazed at its rust-colored surface and wondered, could it ever be like Earth? Could it support life, sustain an atmosphere, and become a second home for humanity? The concept of terraforming Mars has captured the imagination of scientists, visionaries, and storytellers alike. Terraforming, the process of transforming an inhospitable world into one capable of supporting human life, is no longer confined to science fiction. Today, it's the subject of serious research and debate. Mars is cold, barren, and has an atmosphere that's less than 1% the density of Earth's. Its surface is bombarded by radiation, and liquid water can't exist for long due to low atmospheric pressure. Yet beneath these challenges lies potential, an entire planet waiting for us to unlock its secrets. Why Mars? Among all the planets in our solar system, Mars is the most promising candidate for terraforming. It's relatively close to Earth, has polar ice caps, and even shows evidence of ancient rivers and lakes. These features make it an ideal starting point for humanity's first steps in planetary engineering. But transforming Mars won't be easy. It's a colossal undertaking that requires advances in technology, immense resources, and cooperation on a scale never seen before. From warming the planet to thickening its atmosphere, the challenges are as vast as the Martian plains themselves. Before diving into the specifics, it's essential to address the ethical questions. Should we terraform Mars simply because we can? What responsibility do we have to preserve the planet's natural state? These are the questions that must guide our vision as we embark on this incredible journey. Terraforming Mars isn't just about creating a new home for humanity. It's a test of our ingenuity, resilience, and ability to adapt to the unknown. It's about exploring the limits of what's possible and pushing beyond them to build a future among the stars. As we explore this full guide to terraforming Mars, we'll look at the science, the strategies, and the challenges involved in turning this dream into reality. From creating an atmosphere to sustaining life, each step brings us closer to transforming the red planet. This isn't just a story about Mars, it's a story about us. Our curiosity, our drive to survive, and our hope for a better tomorrow are all reflected in the effort to terraform another world. So let's take a closer look at what it takes to transform Mars from a frozen desert into a thriving, habitable planet. It all begins with understanding the science, the vision, and the sheer ambition behind this unprecedented endeavor. Terraforming Mars begins with a clear understanding of what the term truly means. At its core, terraforming involves altering a planet's environment to make it more Earth-like, capable of supporting human life. It's a blend of science, engineering, and vision, all working together to reshape an alien world. Key to this process is creating a stable atmosphere, one that can retain heat and protect against harmful radiation. On Mars, this means developing strategies to thicken its thin, carbon dioxide-dominated atmosphere. This initial step is crucial for building the foundation of a habitable environment. The principles behind terraforming focus on leveraging natural resources whenever possible. From utilizing Martian ice to releasing trapped gases in the soil, the goal is to minimize reliance on materials transported from Earth. Efficiency and sustainability are at the heart of these efforts. Another fundamental aspect is energy. Mars lacks the geothermal and atmospheric dynamics that Earth has, so external energy sources are essential. Solar energy, nuclear reactors, and other innovative technologies will be required to power this planetary transformation. Terraforming isn't just about large-scale engineering. It's also about understanding the delicate balance of planetary ecosystems. Even small changes can have cascading effects, which is why each step must be calculated and deliberate. Missteps could lead to irreversible consequences. Adapting Mars to support human life involves replicating key processes found on Earth. From the water cycle to the generation of breathable air, these natural systems must be recreated or simulated on Mars. Achieving this requires deep knowledge of planetary science and innovative problem-solving. One of the guiding principles is patience. Terraforming is not an overnight process. It could take centuries or longer. While immediate results may be limited, the long-term vision of transforming Mars keeps the effort grounded and focused. A central challenge lies in making Mars warm enough to support liquid water. Without a functioning water cycle, efforts to sustain life will falter. The interplay of temperature, Atmospheric pressure and sunlight is a critical puzzle to solve. Creating a magnetic shield for Mars may also play a pivotal role in terraforming. Without one, solar winds will continue to strip away any atmosphere that's built. This adds another layer of complexity to an already ambitious goal. While the principles of terraforming are rooted in science, they also demand creativity and imagination. Solutions must account for Mars' unique conditions while adapting existing Earth-based technologies. Each innovation could pave the way for breakthroughs in planetary engineering. It's also vital to consider the impact of introducing Earth-based organisms to Mars. Microbes and plants could play a role in generating oxygen and altering soil composition. However, the risks of unintended consequences must be carefully managed. At its heart, the definition and principles of terraforming are about giving humanity a chance to thrive on another world. It's a bold experiment in survival, expansion, and adaptation. Every decision made during this process will shape not only Mars but also our understanding of what's possible in the universe. Mars' atmosphere is vastly different from Earth's, and understanding its composition is essential for terraforming. It's made up primarily of carbon dioxide, with only trace amounts of oxygen and nitrogen. This thin atmosphere provides almost no protection from radiation or meteor impacts. One of the biggest challenges is the atmosphere's low pressure, which is less than 1% of Earth's at sea level. This makes it impossible for liquid water to exist on the surface for extended periods. Increasing atmospheric pressure is a key objective in the terraforming process. Mars' climate is another hurdle, with temperatures averaging around -60 degrees Celsius. These frigid conditions are caused by the planet's distance from the Sun and its thin atmosphere, which cannot retain heat effectively. Creating a warmer environment is critical for any long-term human presence. The planet's lack of a strong magnetic field further complicates matters. Without this natural shield, solar winds strip away the atmosphere over time. This constant erosion must be addressed to ensure the sustainability of any terraformed environment. Dust storms are a unique feature of the Martian climate, sometimes enveloping the entire planet. These storms block sunlight and disrupt surface operations, making them a significant consideration for future settlers. Understanding and mitigating their impact is vital for survival. Mars also experiences extreme temperature fluctuations between day and night. This is due to the thin atmosphere's inability to trap heat effectively. Stabilizing these swings will be necessary for creating a more Earth-like climate. Polar ice caps on Mars contain vast amounts of frozen carbon dioxide and water. These ice reserves are both a challenge and an opportunity, as they could be used to thicken the atmosphere and provide essential resources. Unlocking their potential is a major focus of terraforming efforts. The planet's axial tilt and orbit create distinct seasons, but they are far more extreme than those on Earth. Summers are relatively warm in the southern hemisphere, while winters plunge temperatures to even greater lows. This variability must be considered in any large-scale transformation. Mars receives only about half the sunlight Earth does, limiting its natural ability to heat up. Artificial solutions, such as orbital mirrors or greenhouse gas production, will be required to compensate for this lack of solar energy. These technologies will play a central role in climate modification. Atmospheric composition also affects radiation levels on the surface. Without sufficient protection, humans and plants would be exposed to harmful cosmic rays and solar radiation. Thickening the atmosphere to absorb or deflect this radiation is a critical step. Water vapor, a powerful greenhouse gas, is nearly absent in Mars's atmosphere. Introducing water into the atmosphere could significantly aid in warming the planet. This would also support the development of a water cycle, essential for sustaining life. To terraform Mars successfully, its atmosphere and climate must be transformed into systems that work together. Each component, from greenhouse gases to water vapor, plays a role in creating a stable, habitable environment. Understanding these basics lays the groundwork for the monumental task ahead. Mars's surface is a barren, rocky landscape dominated by iron oxide, giving the planet its iconic red color. This iron-rich dust covers much of the surface, creating a fine, powdery layer that can be both a resource and a challenge for terraforming efforts. Beneath this layer lies a variety of minerals that could be key to supporting human habitation. The soil on Mars is toxic by Earth standards, containing perchlorates, which are harmful to humans and plants. Addressing this toxicity will be an essential step in creating arable land. Removing or neutralizing these compounds is a significant obstacle in the quest to establish a sustainable ecosystem. Mars is also home to an abundance of silicon dioxide, similar to what is found in sand on Earth. This material could be used in construction, helping to build habitats and infrastructure. Utilizing local resources reduces the need to transport materials from Earth, making colonization more feasible. Rock formations across the Martian surface reveal evidence of ancient volcanic activity. These volcanic regions are rich in basalt, a type of rock that could be processed for use in construction or even soil enhancement. This volcanic history provides clues about the planet's geological evolution and potential resource availability. The polar regions of Mars contain vast deposits of water and carbon dioxide ice. These reserves could play a critical role in terraforming, as they hold the potential to increase atmospheric pressure and support the development of a water cycle. Unlocking these resources requires careful planning and advanced technology. Mars' surface is riddled with canyons, impact craters, and dry riverbeds, hinting at a time when liquid water flowed across the planet. These features suggest that Mars may once have been more Earth-like, making it an even more compelling candidate for terraforming. Restoring water to these areas could be a long-term goal. Beneath the surface, Mars may harbor significant quantities of frozen water. Subsurface ice deposits could be mined and melted to provide water for human use and to aid in creating a thicker atmosphere. These hidden reserves could prove invaluable to the terraforming process. Dust plays a major role in shaping the Martian landscape, constantly being redistributed by wind and storms. This fine dust not only complicates surface operations, but also poses challenges for machinery and human health. Understanding how to manage or mitigate its effects will be critical for long-term habitation. Radiation exposure is another major concern tied to Mars' surface conditions. Without a protective magnetic field, the ground itself absorbs significant radiation from the sun and space. Building habitats and structures that account for this radiation is a necessary step in creating safe living environments. The surface is also marked by extensive plains and highlands, offering potential locations for settlements. Some regions are more stable and accessible than others, making site selection a vital part of planning for colonization. Identifying areas with the right balance of resources and safety is key. Mineral deposits on Mars, including iron, aluminum, and magnesium, represent valuable resources for construction and manufacturing. These materials could support the development of tools, equipment, and infrastructure needed for a growing colony. Efficient extraction and processing methods will be essential. Every detail of Mars's surface composition presents both opportunities and challenges for terraforming. Understanding its unique properties allows us to plan how to utilize its resources while addressing the risks they pose. Each element of the surface will play a role in transforming the red planet into a new home for humanity. Water is the cornerstone of any terraforming effort, as it is essential for life as we know it. On Mars, the challenge is not just finding water, but making it accessible and sustainable. Without a reliable water source, creating a livable environment is impossible. Mars already has significant amounts of water locked in its polar ice caps and subsurface layers. These reserves could be melted and used to support human habitation and agriculture. Unlocking this frozen resource is one of the first steps in terraforming. Liquid water plays a critical role in regulating temperature and atmospheric conditions. On Earth, oceans and lakes help stabilize climate and generate weather patterns. Introducing water on a large scale to Mars could replicate these effects over time. The presence of water enables the development of a water cycle, which includes evaporation, condensation, and precipitation. This cycle is essential for creating a self-sustaining environment. Establishing this process on Mars would be a major milestone in the terraforming journey. Water is also a key ingredient for producing oxygen through electrolysis. Splitting water into hydrogen and oxygen could help generate breathable air for future settlers. This dual-purpose utility makes water one of the most valuable resources on Mars. Subsurface ice deposits represent a hidden reservoir of potential. By drilling into these layers, it's possible to extract water without disrupting surface operations. This method could provide a steady supply for both immediate use and long-term terraforming goals. Melting the polar ice caps is another option, though it comes with challenges. Releasing too much carbon dioxide from these regions too quickly could create unintended consequences for Mars's climate. A controlled approach is necessary to ensure the process benefits the broader terraforming plan. Introducing water to the Martian surface also lays the groundwork for agriculture. Plants not only require water to grow but also play a role in producing oxygen and stabilizing the soil. This makes water an essential element for both human survival and ecosystem development. Water's thermal properties can help mitigate the extreme temperature swings on Mars. By absorbing heat during the day and releasing it at night, bodies of water could create more stable living conditions. This effect would be particularly important for early settlements. Transporting water from other celestial bodies, such as icy asteroids, is another strategy. While resource-intensive, this approach could supplement Mars' existing reserves. Such efforts would require advanced technology and careful coordination. Without water, it's impossible to imagine Mars supporting even the simplest forms of life. Whether for drinking, farming, or industrial processes, water is a fundamental requirement. Its availability will shape every aspect of Mars transformation. Every step of terraforming, from creating an atmosphere to supporting life, depends on water. Its importance cannot be overstated, as it is the foundation upon which a habitable Mars will be built. Unlocking its full potential will be one of humanity's greatest achievements. Carbon dioxide is one of the most abundant resources on Mars, and it plays a central role in any terraforming strategy. The planet's atmosphere is already composed of over 95% carbon dioxide, but it's far too thin to provide the greenhouse effect needed for warming. Thickening this atmosphere is a critical first step toward creating a habitable environment. Greenhouse gases trap heat, making them essential for raising the planet's temperature. By increasing the concentration of these gases, Mars could retain more heat from the sun, warming its surface. This process would make it possible to sustain liquid water and support life. Releasing the carbon dioxide trapped in Mars's soil and polar ice caps could provide an immediate boost to atmospheric pressure. Techniques like heating the surface with giant mirrors or using controlled explosions could trigger the release of these gases. This would be the foundation for building a thicker, warmer atmosphere. In addition to carbon dioxide, other greenhouse gases like methane and water vapor could amplify the warming effect. Methane is especially potent and could be produced through industrial processes or introduced artificially. These gases would work in tandem to accelerate Mars transformation. Creating greenhouse gases on Mars would likely involve industrial-scale operations. Factories designed to release gases like carbon dioxide and methane into the atmosphere could help jumpstart the warming process. These facilities would require significant energy, but offer a direct path to climate modification. The gradual thickening of the atmosphere would reduce the temperature extremes that currently dominate Mars. By retaining heat during the day and slowing heat loss at night, a denser atmosphere could stabilize surface conditions. This would make the planet more suitable for human habitation and agriculture. However, relying on greenhouse gases comes with challenges. Introducing too much too quickly could create runaway warming or other unintended effects. A controlled approach is essential to balance the pace of warming with the planet's ability to adapt. Some greenhouse gases could be imported from other locations, such as asteroids or moons rich in methane or ammonia. Transporting these gases would be a massive logistical challenge, but could provide a boost to Mars' terraforming efforts. This strategy might supplement local resources and speed up the process. Carbon dioxide is also vital for plant life, as it serves as a raw material for photosynthesis. By introducing plants or engineered organisms that thrive on carbon dioxide, the atmosphere could be further enriched with oxygen over time. This dual benefit makes it an attractive resource for long-term sustainability. The interplay between carbon dioxide, water vapor, and other gases would create a dynamic and evolving climate system. Each addition to the atmosphere would influence the planet's temperature, pressure, and weather patterns. Understanding these interactions is key to managing the terraforming process effectively. While greenhouse gases are essential for warming Mars, they're only one part of the equation. They must be combined with other efforts, such as creating magnetic shields and introducing water, to ensure the atmosphere remains stable. This multifaceted approach will maximize the likelihood of success. Carbon dioxide and greenhouse gases are the catalysts for Mars transformation. They hold the potential to turn a frozen wasteland into a planet teeming with possibilities. Harnessing them effectively is one of the greatest challenges and opportunities of terraforming Mars. Thickening Mars' atmosphere is a fundamental step toward making the planet more hospitable. A denser atmosphere can trap heat, provide protection from radiation, and support the presence of liquid water. Achieving this requires a combination of scientific ingenuity and large-scale engineering. One approach is to release the carbon dioxide currently trapped in the Martian polar ice caps and soil. By artificially heating these areas, stored gases could be liberated, boosting atmospheric pressure. Technologies such as orbital mirrors or localized nuclear detonations might be used to achieve this. Volcanic simulation is another strategy to increase atmospheric density. Mimicking volcanic activity could release large quantities of greenhouse gases, including carbon dioxide and water vapor. This method seeks to replicate natural processes that have shaped atmospheres on other planets. Introducing ammonia-rich asteroids into Mars's atmosphere is also a possibility. Ammonia acts as a powerful greenhouse gas and could contribute to thickening the air. Redirecting and safely delivering these asteroids to the planet would require advanced spaceflight capabilities. Another idea involves large-scale industrial production of gases directly on Mars. Factories could generate carbon dioxide, methane, or other greenhouse gases from Martian resources. This approach provides a controllable and steady way to enhance the atmosphere over time. Hydrofluorocarbons, which are highly effective greenhouse gases, could also be introduced. Although they don't occur naturally on Mars, these gases could be manufactured or transported from Earth. Their potency makes them a valuable tool for rapidly warming the planet. A magnetic shield positioned at the Mars-Sun L1 point could indirectly aid atmospheric thickening. By deflecting solar winds, such a shield would prevent the continuous stripping away of gases. This would allow any newly introduced atmosphere to remain stable over the long term. Incorporating bioengineered organisms could provide a biological route to atmospheric thickening. Certain microbes or plants might be designed to release gases as they metabolize the Martian environment. This natural approach complements industrial methods and could help balance the atmosphere. Building artificial structures such as domes or atmospheric generators might also create localized areas of increased pressure. Over time, these zones could expand as the planet's atmosphere grows denser. This step-by-step process could make early colonization efforts more feasible. Solar-powered heaters distributed across the planet could gradually warm the surface and release trapped gases. These devices would be energy efficient and scalable, allowing for widespread application. The gradual warming they provide would contribute to a thicker and more stable atmosphere. Transporting gases directly from Earth or other celestial bodies represents a more immediate, though resource-intensive, option. While challenging, this approach could provide a controlled influx of atmospheric material. It might serve as an initial boost while other systems are being developed. Thickening Mars' atmosphere will take time and coordination across multiple strategies. By combining natural processes, advanced technology, and innovative thinking, humanity can transform the thin Martian air into a protective and life-supporting layer. Each step in this process brings us closer to a truly habitable planet. Mars holds vast amounts of carbon dioxide locked away in its soil and rocks. Releasing this trapped CO2 could significantly increase atmospheric pressure and enhance the greenhouse effect. Unlocking these reserves is one of the most practical first steps in terraforming the planet. One method involves heating the surface to encourage the release of carbon dioxide. Technologies like giant orbital mirrors could reflect sunlight onto specific areas, warming the ground and triggering the release of gases. This process would mimic natural heating but on a much larger scale. Another approach is to use targeted nuclear detonations beneath the surface. These controlled explosions would break apart subsurface rock layers, releasing the CO2 trapped within. While controversial, this method offers a rapid way to access large amounts of gas. Drilling into the Martian crust is another option to access CO2 reserves deep underground. By tapping into pressurized pockets of gas, it's possible to bring them to the surface. This technique would require advanced mining equipment capable of operating in Mars's harsh environment. Localized heating devices such as ground-based lasers or solar concentrators could also be used to release carbon dioxide. These tools would focus energy on specific areas, providing a precise and scalable way to liberate gas. This method avoids the risks associated with large-scale explosions. Mars' polar ice caps contain significant amounts of frozen carbon dioxide, which could be released by targeted melting. This could be achieved using orbital mirrors, localized heaters, or even by redirecting sunlight through artificial means. Melting these reserves would also contribute to warming the planet. Chemical processes could also be employed to extract CO2 from Martian soil. Specialized compounds or engineered microbes might break down the soil to release stored gases. This approach could be integrated with other terraforming methods to maximize efficiency. Releasing CO2 from the soil might also generate secondary benefits, such as uncovering additional resources. Minerals or water trapped alongside the gas could become accessible for use in human settlements. This makes gas extraction a multi-purpose effort. Managing the rate of release is crucial to avoid destabilizing the planet's surface or atmosphere. A controlled, gradual release allows for better monitoring and adjustment of Mars's climate. Sudden or excessive gas emissions could lead to unintended consequences, such as violent weather patterns. The scale of this effort will require coordination between robotic systems and human oversight. Autonomous machines could work across large swathes of the planet, drilling, heating, and extracting gas. These operations would lay the groundwork for larger-scale atmospheric changes. Once released, the carbon dioxide would begin contributing to atmospheric pressure and warmth. The thicker air would improve conditions for liquid water to exist on the surface and for future human activities. This marks a pivotal step in the journey toward a habitable Mars. Releasing trapped CO2 from the soil is not just about adding gas to the atmosphere, it's about creating a cascading effect. With more CO2 in the air, the planet warms, water flows, and a new chapter begins in shaping Mars for human life. This transformation starts deep beneath the surface. Importing gases from other celestial bodies is an ambitious but potentially transformative approach to terraforming Mars. By bringing in greenhouse gases like ammonia or methane, we could rapidly increase atmospheric pressure and warmth. This strategy complements efforts to use local Martian resources. One potential source of gases is the outer planet's moons, such as Titan, which has a thick atmosphere rich in methane. Extracting these gases and transporting them to Mars would be a massive undertaking, but could provide a significant boost to the terraforming process. This approach leverages the abundance of resources within our solar system. Asteroids and comets are another option, as many of them contain frozen ammonia, water, and other gases. Redirecting these objects to collide with Mars or releasing their contents in orbit could deliver large quantities of greenhouse materials. This method has the added benefit of contributing water and other valuable compounds. Transporting gases from Earth, while expensive and limited in scale, could serve as a starting point. Early shipments of high-impact gases like hydrofluorocarbons might provide an initial boost to Mars' atmosphere. This approach is likely to be more practical during the early phases of terraforming. Spacecraft equipped with advanced propulsion systems would be key to this process. These vessels could capture gas-rich objects, process them during transit, and release the gases upon arrival at Mars. The development of such technology would mark a major milestone in interplanetary engineering. Another possibility involves mining the atmospheres of gas giants like Jupiter or Saturn. Their upper layers contain hydrogen, helium, and ammonia, which could be extracted and transported. While technically challenging, these sources offer vast amounts of raw material. Releasing imported gases in orbit around Mars could allow them to slowly integrate into the atmosphere. This controlled approach minimizes risks and provides a gradual increase in pressure. By carefully managing the dispersion, we can ensure the gases enhance Mars' climate effectively. The logistics of transporting gases involve numerous challenges, from capturing materials in space to safely delivering them to Mars. Each mission would require precise planning to avoid wasting resources or creating unintended consequences. Success depends on efficient coordination and advanced spacecraft. Ethical and environmental considerations also come into play when sourcing gases from other celestial bodies. Altering the composition of asteroids or moons raises questions about the broader impact on the solar system. Balancing these concerns with the need for resources is an ongoing challenge. The introduction of foreign gases could also have chemical interactions with Mars' existing atmosphere. Predicting and managing these effects is crucial to ensure the planet's transformation proceeds smoothly. This requires detailed modeling and experimentation to anticipate potential outcomes. By importing gases, we not only accelerate the terraforming process, but also create opportunities for new scientific discoveries. Studying the behavior of these materials in Mars's environment expands our understanding of atmospheric chemistry and planetary engineering. Each mission contributes to our growing expertise. Importing gases from other sources represents humanity's willingness to think beyond planetary boundaries. It showcases our ability to harness resources from across the solar system to create a habitable world. This bold approach exemplifies the scale of innovation required to reshape Mars. Mars lacks a magnetic field, leaving its atmosphere vulnerable to erosion by solar winds. An artificial magnetic field could shield the planet, preventing the loss of gases and enabling a thicker atmosphere to form. This would be a critical step in creating a more stable and habitable environment. One proposed method is to place a magnetic shield at the Mars-Sun L1 point, a location in space where gravitational forces are balanced. This shield could deflect solar winds before they reach Mars, preserving the atmosphere over time. Such a system would act as a planetary-scale umbrella. This magnetic shield could be powered by a massive array of solar panels or nuclear energy sources. Harnessing energy in space would allow for the continuous operation of the shield, ensuring its effectiveness. Advanced energy storage systems might also be required for consistent functionality. Another approach involves creating smaller, localized magnetic fields on Mars itself. These fields could be generated around key habitats or regions, offering protection in specific areas. Over time, these zones could expand as the atmosphere grows denser. Plasma-based technologies are also being explored as a potential solution. By releasing streams of charged particles, an artificial magnetosphere could be created to envelope the planet. This method would mimic natural magnetic fields seen around other celestial bodies. Building the infrastructure for an artificial magnetic field requires innovation in materials science. The equipment must withstand harsh conditions, including radiation and extreme temperatures. Lightweight, durable materials will be essential for the success of this endeavor. Such systems would need constant monitoring and maintenance to ensure they operate effectively. Robotic platforms or automated drones could perform repairs and adjustments, reducing the need for human intervention. This approach allows for sustained operation over decades or even centuries. Creating a magnetic field is not just about atmospheric retention, it also protects against harmful radiation. With a shield in place, the surface of Mars becomes far safer for humans, plants, and other life forms. This dual benefit makes it a cornerstone of terraforming efforts. The introduction of an artificial magnetic field might also influence other aspects of the planet's transformation. For instance, it could enable the development of a water cycle by preventing evaporation into space. This interconnected impact highlights the importance of addressing multiple challenges simultaneously. While ambitious, the concept of an artificial magnetic field is rooted in established science. Similar principles are already used to protect satellites and spacecraft from radiation. Scaling this technology to a planetary level is the next logical step in its evolution. The success of such a project would mark a major milestone in humanity's ability to engineer entire planets. It represents a leap in our understanding of how to adapt hostile environments for human survival. Mars would serve as both a proving ground and a symbol of what's possible. An artificial magnetic field is more than just a technical solution. It's a foundation for building a future on Mars. With this protective barrier in place, the planet can retain the atmosphere it needs, paving the way for a habitable and thriving world. Mars faces a fundamental issue with atmospheric retention due to its weak gravity and lack of a magnetic field. Even if gases are introduced, the planet struggles to hold onto them over time. This poses a major challenge for creating a stable, long-term atmosphere. Solar winds relentlessly strip away Mars's atmosphere, particularly lighter gases like hydrogen and helium. Without a protective barrier, these particles are lost to space, undoing progress in thickening the air. Addressing this loss is crucial for any terraforming plan. Low gravity also contributes to atmospheric escape, as it makes it easier for gas molecules to reach escape velocity. Even heavier gases like carbon dioxide are at risk over extended periods. Overcoming this limitation requires innovative solutions to sustain atmospheric density. Dust storms, a common feature of Mars, add another layer of complexity. These storms can disrupt atmospheric stability and redistribute heat unevenly across the planet. Understanding their impact is critical for maintaining a balanced and consistent climate. Temperature fluctuations between day and night exacerbate the problem by causing rapid expansion and contraction of gases. This can lead to localized losses and makes it harder to establish a steady atmospheric state. Stabilizing temperatures is a key priority in combating this challenge. Radiation from the sun and cosmic rays further degrades the atmosphere. High-energy particles break apart gas molecules, reducing their effectiveness in trapping heat. A denser atmosphere would offer some protection, but the problem must be addressed early in the terraforming process. Long-term sustainability is also affected by the lack of natural replenishment cycles. Unlike Earth, Mars lacks volcanic activity or biological processes to continuously produce atmospheric gases. Artificial systems must fill this gap to maintain atmospheric levels. The planet's low atmospheric pressure makes it difficult to create a self-sustaining water cycle. Water vapor escapes into space more easily in such conditions, preventing the formation of stable clouds and precipitation. Enhancing pressure is essential for overcoming this hurdle. Imported or manufactured gases could also interact unpredictably with the existing Martian environment. Chemical reactions with the soil or other gases might reduce their effectiveness or lead to unintended consequences. Careful monitoring and testing are required to prevent setbacks. Achieving the right balance of gases is another challenge. Too much of one type, like carbon dioxide, could lead to extreme greenhouse effects or toxic conditions. Striking the right mix is critical for creating a livable environment. Energy demands for sustaining atmospheric systems are immense. Whether through magnetic shields, gas production facilities, or heating mechanisms, the process requires constant power. Ensuring a reliable and scalable energy supply is a cornerstone of any atmospheric retention strategy. Despite these challenges, the effort to retain a stable atmosphere on Mars is vital to the success of terraforming. Each obstacle highlights the need for innovative solutions and precise execution. Overcoming these barriers brings humanity one step closer to transforming Mars into a habitable world. Orbital mirrors are a proposed method to warm Mars by reflecting sunlight onto specific regions of the planet. These massive structures would orbit above the surface, redirecting solar energy to heat the ground and release trapped gases. This approach could accelerate the process of atmospheric thickening. The mirrors would be constructed using lightweight, reflective materials capable of withstanding the harsh conditions of space. Their size and position would need to be carefully calculated to ensure they effectively target key areas on the Martian surface. Precision in deployment is critical for maximizing their impact. One primary goal is to melt the carbon dioxide ice in the polar caps, releasing greenhouse gases into the atmosphere. This would increase atmospheric pressure and contribute to a warming effect. Orbital mirrors offer a controlled way to achieve this without requiring extensive surface infrastructure. Another potential use is to create localized hotspots where conditions are more favorable for human activity or experimentation. These zones could serve as testing grounds for agriculture, habitat construction, or further terraforming techniques. By concentrating sunlight, orbital mirrors make these experiments feasible. The mirrors could also aid in establishing a water cycle by warming areas where subsurface ice is present. Melting this ice could release water vapor into the atmosphere, jump-starting processes like cloud formation and precipitation. This adds another layer to their utility in terraforming efforts. Energy efficiency is one of the advantages of using orbital mirrors. Once deployed, they rely solely on the sun's energy, eliminating the need for additional power sources. This makes them a sustainable option for long-term warming efforts on Mars. However, the construction and transportation of these mirrors pose significant logistical challenges. They would need to be assembled in space or transported in parts from Earth, requiring advanced engineering and coordination. The scale of the project would push current space technology to its limits. Orbital stability is another concern, as the mirrors must remain precisely positioned to be effective. They would require constant adjustments to counteract gravitational forces and maintain their targeted focus. This could involve automated systems or regular interventions by robotic platforms. Potential risks include unintended environmental effects, such as overheating certain areas or destabilizing existing ice deposits. Careful modeling and testing would be needed to predict and mitigate these outcomes. Ensuring that their impact aligns with broader terraforming goals is crucial. The durability of the mirrors in the harsh Martian environment also raises questions. Exposure to micrometeoroids, radiation, and temperature extremes could degrade their performance over time. Developing materials that can endure these conditions is a key challenge. Orbital mirrors could also serve dual purposes, such as generating solar energy for use in surface operations. By integrating photovoltaic panels, these structures might provide both heat and power. This multifunctional approach enhances their value in a Martian context. Despite their challenges, orbital mirrors represent a bold and innovative solution for warming Mars. They leverage the abundant energy of the Sun to transform the planet's surface and atmosphere, paving the way for further advancements in terraforming. These structures embody the scale of vision needed to turn Mars into a habitable world. Producing greenhouse gases directly on Mars is a critical strategy for warming the planet and thickening its atmosphere. By manufacturing gases like carbon dioxide, methane, and hydrofluorocarbons, we can amplify the greenhouse effect and create a more stable climate. This approach utilizes both local resources and innovative technologies. Factories could be established on the surface to generate greenhouse gases from Martian materials. Carbon dioxide, abundant in the soil and polar caps, is an obvious starting point. These facilities would extract and release the gas into the atmosphere on a large scale. Methane, a highly effective greenhouse gas, could be produced using chemical reactions involving hydrogen and carbon from Martian resources. This process would require a reliable energy source, but offers significant benefits in terms of warming potential. Methane's longevity in the atmosphere also makes it a valuable addition. Hydrofluorocarbons, while synthetic, are extremely powerful at trapping heat. These gases could be manufactured on Mars using imported raw materials or advanced chemical processes. Their high efficiency means smaller quantities are needed to achieve meaningful effects. To power these production facilities, renewable energy sources like solar or nuclear could be employed. Solar panels would take advantage of Mars's sunlight, while compact nuclear reactors could provide consistent energy. These power systems are essential for maintaining continuous gas production. Another approach involves bioengineered organisms designed to emit greenhouse gases as they metabolize Martian materials. Microbes or algae could be introduced to specific areas, producing gases while also preparing the soil for future agricultural use. This biological solution complements industrial methods. Robotic systems would play a major role in setting up and operating gas production facilities. Autonomous machines could extract resources, monitor outputs, and maintain equipment, reducing the need for human presence. This automation makes large-scale production more feasible in the early stages. Greenhouse gas production must be carefully managed to avoid unintended consequences. Overproducing gases could lead to runaway warming or create localized environmental imbalances. Continuous monitoring and adjustment are necessary to ensure the planet evolves in a controlled manner. In addition to warming the planet, these gases contribute to atmospheric pressure, making conditions more suitable for liquid water. A thicker atmosphere also provides better protection from radiation, a key factor for future human habitats. These dual benefits highlight the importance of greenhouse gas production. Collaboration between industrial and biological approaches could accelerate the process. While factories handle large-scale gas output, bioengineered organisms could operate in remote or inaccessible areas. This multi-pronged effort increases the overall efficiency of terraforming. Imported equipment and materials might initially support these efforts, but the long-term goal is to make the process self-sufficient. Using Martian resources ensures sustainability and reduces reliance on Earth. This transition is critical for the success of a permanent colony. Producing greenhouse gases on Mars is more than a technical challenge. It's a foundational step in creating a habitable world. These gases hold the key to transforming the planet's climate, unlocking the potential for a thriving ecosystem and future human settlement. Each molecule released brings Mars closer to becoming a new home. Simulating volcanic activity on Mars is another innovative approach to generating heat and releasing greenhouse gases. Volcanic processes naturally emit carbon dioxide, water vapor, and other gases that contribute to atmospheric thickening. Mimicking these effects could accelerate Mars' transformation into a habitable environment. Artificial volcanic systems would require advanced engineering to replicate the intense heat and pressure of natural eruptions. By heating subsurface materials, these systems could release trapped gases and warm the surrounding area. This localized warming could kickstart broader atmospheric changes. One method might involve drilling into the Martian crust to access geothermal energy. High-temperature processes could then be initiated to vaporize minerals and release carbon dioxide. This approach taps into the planet's existing geology, minimizing the need for external resources. Chemical reactions triggered by these artificial eruptions could also produce additional gases. For example, combining subsurface compounds with water or other reactants might yield methane or sulfur dioxide. These gases would further enhance the greenhouse effect and contribute to warming. Volcanic simulation could focus on regions with a history of geological activity, such as Tharsis or Elysium. These areas are more likely to contain the right conditions for gas release and heat generation. Targeting these sites ensures maximum impact with minimal effort. The heat generated by artificial volcanic activity could also be used to melt nearby ice deposits. This would release water vapor into the atmosphere, supporting the development of a water cycle. It could also create liquid water reservoirs for future human use. Automated systems would be essential for operating these volcanic simulations. Robots equipped with drills, heaters, and sensors could work independently to trigger eruptions and monitor their effects. This reduces the risks associated with human involvement in these high-temperature environments. One challenge is controlling the scale of these simulated eruptions. Too much heat or gas release at once could destabilize the surrounding environment or create hazardous conditions. Careful planning and real-time adjustments would be necessary to manage these risks. Simulated volcanoes might also have applications beyond heating and gas release. The minerals brought to the surface could be harvested for construction or other uses. This dual-purpose approach adds value to the effort and supports broader colonization goals. The energy demands for volcanic simulation are significant, requiring robust power sources. Nuclear reactors or concentrated solar energy could provide the consistent output needed for these operations. Ensuring reliable energy is critical for sustaining this process over time. Volcano simulation aligns with the larger goal of creating a self-sustaining atmosphere on Mars. By mimicking natural geological processes, this method builds upon the planet's existing potential. It's an example of leveraging Mars' unique characteristics to drive terraforming forward. Each simulated eruption represents progress in warming Mars and thickening its atmosphere. These efforts bring the planet closer to supporting life, combining science, engineering, and creativity to reshape an entire world. Mars's volcanic legacy could become a key to its future transformation. Nuclear energy offers a powerful and consistent solution for warming Mars and supporting terraforming efforts. By harnessing the immense heat generated through nuclear reactions, localized warming could be achieved on the planet's surface. This technology has the potential to drive significant changes in Mars' climate. One approach involves deploying small nuclear reactors across key regions of Mars. These reactors could provide heat to melt ice, release trapped carbon dioxide, and contribute to atmospheric thickening. Their compact size makes them ideal for remote and harsh environments. Another method is the use of controlled nuclear detonations beneath the surface. These explosions could release heat and gases from the Martian crust, triggering localized warming. While controversial, this strategy could accelerate the release of essential greenhouse gases. Nuclear power could also be used to energize factories that produce greenhouse gases. The steady and reliable energy output from reactors would ensure uninterrupted operation of these facilities. This dual-purpose application highlights the versatility of nuclear energy on Mars. For long-term warming, nuclear thermal generators could be placed strategically near polar ice caps. The heat from these systems would gradually melt ice, releasing water vapor and carbon dioxide into the atmosphere. This slow and controlled process minimizes risks while enhancing atmospheric density. Compact nuclear reactors could power drilling operations to access geothermal energy or subsurface resources. These operations are critical for releasing trapped gases and initiating other terraforming processes. The efficiency of nuclear energy ensures these efforts remain sustainable over time. Safety is a major consideration when deploying nuclear technology on Mars. Reactors must be designed to withstand harsh conditions and avoid contamination of the Martian environment. Advanced shielding and fail-safe mechanisms are essential for minimizing risks. Nuclear energy also provides a reliable backup for other warming strategies. While solar mirrors or industrial systems depend on environmental conditions, Nuclear reactors deliver consistent output regardless of weather or location. This reliability is crucial for sustained terraforming efforts. Portable nuclear devices could be used to target specific areas in need of immediate warming. These mobile systems allow for flexibility in addressing localized challenges, such as melting isolated ice deposits or heating small settlements. Their adaptability makes them an asset in early terraforming stages. Energy from nuclear reactions might also support research and development of other terraforming technologies. For example, high-temperature experiments could be conducted to explore innovative ways of altering Mars' surface or atmosphere. Nuclear power enables these advancements by providing the necessary energy. In addition to warming, nuclear energy can support the infrastructure needed for human survival on Mars. It could power habitats, life support systems, and manufacturing facilities, creating a foundation for future settlements. Its multifaceted role makes it indispensable for long-term colonization. Nuclear energy represents one of the most potent tools for transforming Mars. Its ability to deliver heat, power, and versatility aligns perfectly with the challenges of terraforming. By integrating nuclear technology into the overall strategy, Mars can take another step toward becoming a habitable world. Balancing temperature increases on Mars is essential to ensure that the planet warms gradually and sustainably. Rapid or uncontrolled warming could lead to unpredictable consequences, such as extreme weather or surface destabilization. Careful monitoring and adjustment are required at every step of the process. A gradual approach to warming allows scientists to study and adapt to the planet's responses. By increasing temperatures in stages, we can avoid overwhelming Mars' fragile environment. This strategy provides time to implement corrections if unexpected issues arise. Overheating certain regions could disrupt the distribution of resources like water and carbon dioxide. For example, melting too much ice at once might create floods or reduce long-term reserves. A balanced plan ensures these resources are managed efficiently and preserved for future use. Localized warming techniques such as orbital mirrors or ground-based heaters offer precise control over temperature increases. These methods allow specific areas to be targeted without affecting the entire planet. This precision is crucial for creating habitable zones while maintaining broader stability. The interplay between temperature and atmospheric pressure must also be carefully managed. As temperatures rise, gases are released into the atmosphere, increasing pressure. Ensuring these processes occur in harmony is vital for achieving a stable climate. Too much warming could also release harmful chemicals trapped in the Martian soil, such as perchlorates. These substances could pose risks to human health and environmental stability. Monitoring the release of such compounds is a key part of balancing temperature increases. Establishing early warning systems to detect signs of overheating or environmental imbalance is critical. Sensors and satellites could track temperature changes, gas levels, and other key indicators. This data enables real-time adjustments to maintain stability. Energy sources used for warming must also be managed carefully to avoid contributing to excessive heat. Technologies like nuclear reactors or greenhouse gas factories should operate within controlled parameters. This ensures they contribute to the process without causing unintended consequences. Temperature increases should align with broader goals, such as developing a water cycle or supporting vegetation growth. Overheating could hinder these efforts by creating conditions that are too extreme for life to thrive. Balancing warmth with habitability is the ultimate objective. Collaboration across different warming methods can provide redundancy and flexibility. For instance, if one approach leads to excessive heat, others can be scaled back to compensate. This coordination creates a more resilient system for managing the planet's transformation. Balancing temperatures also requires long-term planning to account for changes over decades or centuries. Mars' environment will continue to evolve as terraforming progresses, and strategies must adapt accordingly. Anticipating future challenges is as important as addressing current ones. Creating a balanced temperature increase is not just about technical precision, it's about ensuring Mars remains a viable candidate for life. Every degree of warming must serve a purpose, contributing to the gradual transformation of a cold, barren world into a place where humanity can thrive. The polar ice caps of Mars hold vast amounts of frozen carbon dioxide and water, making them a critical resource for terraforming. Melting these ice caps could release greenhouse gases and water vapor, contributing to atmospheric thickening and climate warming. Unlocking this potential is a key early step in transforming the planet. One method to melt the ice caps involves directing sunlight onto them using orbital mirrors. These mirrors would focus solar energy onto the frozen regions, increasing their temperature and triggering the release of trapped gases. This approach allows for precise control over which areas are targeted. Localized heating systems on the ground could also be deployed to accelerate the melting process. Solar-powered heaters or nuclear thermal devices could concentrate energy directly on the ice. These systems would work in conjunction with larger-scale strategies to ensure efficiency. As the ice melts, the released carbon dioxide would add to the planet's atmosphere, boosting pressure and enhancing the greenhouse effect. This creates a feedback loop where warming leads to more gas release, which in turn increases the warming. Managing this cycle is crucial for maintaining stability. The release of water vapor from the ice caps could also help establish a water cycle on Mars. This would involve evaporation, condensation, and precipitation, laying the groundwork for clouds and potentially rainfall. A functioning water cycle is essential for long-term habitability. Careful monitoring is needed to avoid melting too much ice too quickly. Rapid melting could lead to floods or unstable conditions in the surrounding regions. A gradual approach ensures that the process remains controlled and benefits the broader terraforming plan. Melting the polar ice caps might also expose subsurface materials and minerals that could be useful for future settlements. These newly accessible resources would add value to the effort, supporting both terraforming and colonization goals. This dual benefit makes the ice caps a focal point of early interventions. The energy requirements for melting such large volumes of ice are significant. Efficient systems powered by solar or nuclear energy would be essential to sustain the process. Reliable energy sources ensure that the melting proceeds without interruption. Robotic systems could be deployed to monitor and manage the melting process in real time. These machines would track temperature changes, gas release, and water flow, ensuring the effort remains on target. Automation reduces the risks associated with human intervention in such challenging conditions. Melting the ice caps could also have unforeseen environmental effects, such as altering wind patterns or triggering dust storms. These changes must be anticipated and mitigated to prevent disruptions to other terraforming efforts. A holistic approach to monitoring is key. Once the ice caps begin to melt, their contribution to warming and atmospheric changes would be significant. They represent one of Mars' largest reservoirs of readily available resources, making them a cornerstone of any terraforming strategy. Unlocking their potential accelerates progress toward a habitable planet. Every step in melting the polar ice caps brings Mars closer to supporting life. The combination of released gases and water vapor sets the stage for atmospheric thickening, temperature increases, and a functioning ecosystem. These frozen reserves hold the key to Mars transformation. Transporting ice from asteroids is an ambitious strategy to supply Mars with water and contribute to its terraforming efforts. Many asteroids in the solar system contain significant amounts of frozen water, ammonia, and other valuable compounds. Redirecting these ice-rich objects to Mars could provide both immediate and long-term benefits. To achieve this, advanced propulsion systems would be used to alter the orbits of selected asteroids. These systems would guide the objects toward Mars, either to impact the surface or release their materials in orbit. Precision in trajectory control is essential to ensure a safe and effective delivery. One approach involves capturing smaller asteroids and placing them in orbit around Mars. This allows for controlled melting and gradual release of water vapor into the atmosphere. These orbiting reservoirs could act as a steady source of resources over time. Asteroids could also be directed to specific regions on Mars, such as polar areas or proposed settlement sites. Upon impact, the released water and other materials would be readily available for use. This targeted approach maximizes the value of each delivery. Some missions might involve mining ice directly from asteroids and transporting it to Mars in smaller, manageable quantities. This requires the development of specialized extraction and containment systems to ensure the ice remains stable during transit. Such missions offer a more controlled alternative to asteroid redirection. Ammonia contained within some asteroids could act as a powerful greenhouse gas, enhancing Mars's warming process. By combining water delivery with atmospheric benefits, these objects play a dual role in terraforming. The chemical contributions further accelerate progress toward habitability. The transportation of ice-rich asteroids would require robust shielding to protect against sublimation and fragmentation during the journey. These challenges demand innovative engineering solutions to preserve the integrity of the cargo. Ensuring the ice remains intact is critical for mission success. Potential risks include unintended impacts that could damage the Martian surface or create hazardous conditions. Careful trajectory calculations and fail-safe mechanisms are necessary to mitigate these dangers. Each mission must prioritize safety alongside its objectives. The energy required to redirect asteroids is significant, calling for the use of solar sails, ion thrusters, or nuclear propulsion systems. These advanced technologies provide the precision and efficiency needed for long-distance transport. Energy management is a key factor in mission planning. Collaboration with asteroid mining operations could expand the scope of this strategy. Partnerships with private companies or international agencies could streamline resource acquisition and delivery. This cooperative approach ensures that missions remain cost-effective and sustainable. The introduction of asteroid materials to Mars could also spur new scientific discoveries. Studying the composition of these objects enhances our understanding of the solar system and its resources. Each mission contributes to both terraforming goals and broader knowledge. Transporting ice from asteroids demonstrates humanity's ability to harness resources from across the solar system. By delivering water and greenhouse materials to Mars, this strategy accelerates the transformation of the planet. Each redirected asteroid brings us closer to a habitable future. Beneath the surface of Mars lies a vast reservoir of frozen water, an essential resource for terraforming and human settlement. Extracting this subsurface ice offers a sustainable way to provide water for atmospheric generation, agriculture, and daily survival. Accessing it requires advanced drilling and heating technologies. One method involves using robotic drills to reach deep layers of ice deposits. These machines would operate autonomously, digging through soil and rock to expose the frozen reserves. Their ability to adapt to varying terrain is crucial for successful extraction. Heating systems could be employed to melt the ice in situ, turning it into liquid water that can be pumped to the surface. Solar-powered heaters or nuclear devices provide efficient energy sources for this process. This direct approach minimizes disruption to the surrounding environment. Transporting the extracted water from subsurface reserves to key locations on Mars is another challenge. Pipelines or storage tanks could be used to distribute the water where it's most needed. This infrastructure forms the backbone of a sustainable water supply system. Mapping and identifying areas with high concentrations of subsurface ice is a critical first step. Satellites and ground-penetrating radar provide the data needed to locate the richest deposits. Accurate mapping ensures that resources are used efficiently. Subsurface ice extraction could also release water vapor into the atmosphere, contributing to a thicker and more dynamic climate. This natural byproduct supports broader terraforming goals by adding moisture to the air. It's a small but significant step toward creating a water cycle on Mars. Managing the temperature during extraction is essential to prevent the water from refreezing. Insulated systems and controlled heating ensure that liquid water remains accessible during the process. Precision engineering is key to maintaining flow and usability. Extracting ice at scale requires energy-intensive systems, making reliable power sources a priority. Solar panels, nuclear reactors, or geothermal energy could sustain operations over long periods. Ensuring uninterrupted energy supply is critical for large-scale success. Ice deposits near potential settlement sites offer an immediate advantage, reducing the need for long-distance transport. Establishing colonies close to these reserves simplifies access and supports early habitation efforts. This proximity becomes a factor in site selection. As ice is extracted, the exposed areas might reveal other valuable resources, such as minerals or gases trapped within the layers. These secondary discoveries could enhance the utility of the extraction process. Multi-purpose operations maximize the return on investment. Environmental considerations must also be addressed to avoid destabilizing the surface or causing unintended effects. Over-extraction could lead to sinkholes or erosion, which might disrupt future plans. Sustainable practices ensure the long-term viability of these reserves. Subsurface ice represents one of Mars' most critical natural assets. Its extraction not only supports immediate needs, but also lays the foundation for a thriving, self-sustaining presence on the planet. Each drop of water brings Mars closer to becoming a habitable world. Artificial lakes and rivers on Mars could serve as vital components of its transformation, providing water for ecosystems, agriculture, and human use. These features would also help regulate temperature and support the development of a water cycle. Constructing them involves a combination of engineering and careful environmental management. To create artificial lakes, depressions, or craters could be filled with water extracted from subsurface ice or transported from other sources. These basins would act as reservoirs, storing water for various uses. Their locations must be carefully selected to minimize evaporation and maximize accessibility. Rivers could be formed by channeling water from these lakes, creating networks that distribute water across the surface. Controlled flow systems would ensure that water reaches areas designated for agriculture or settlements. These waterways mimic natural processes, supporting broader terraforming efforts. The introduction of water to the Martian surface could also help stabilize the soil, reducing the impact of dust storms. Moisture binds fine particles, preventing them from being easily carried by the wind. This added stability is a key benefit of artificial lakes and rivers. Heating systems may be necessary to prevent the water from freezing in Mars' cold temperatures. Solar or geothermal heat could be used to maintain liquid water, especially in smaller isolated bodies. These systems ensure the sustainability of artificial water features. Artificial lakes and rivers could also contribute to atmospheric thickening by releasing water vapor into the air. This vapor supports cloud formation and precipitation, essential steps in creating a functioning water cycle. Over time, these processes help shape a more Earth-like climate. Selecting locations for these water features involves studying the Martian terrain and climate. Flat plains, valleys, or ancient riverbeds might provide the ideal foundation for lakes and channels. These natural formations reduce the need for extensive excavation or modification. Water features might also play a role in cooling local temperatures by absorbing heat during the day and releasing it at night. This thermal regulation benefits nearby habitats and agricultural zones. It's a small but important step in creating more stable living conditions. The materials needed to construct dams, channels, or embankments must be sourced locally to reduce transportation costs. Martian soil and rock could be used to build these structures, supporting a sustainable approach. This reliance on native materials ensures that projects are scalable. Establishing ecosystems around these artificial lakes and rivers could enhance their impact. Introducing hardy plants or microorganisms that thrive in wet environments would begin the process of creating life-supporting biomes. These ecosystems contribute to oxygen production and soil enrichment. Maintaining water quality is another important consideration. Systems for filtering and monitoring the water would prevent contamination, ensuring it remains usable for all purposes. These safeguards are critical for supporting life and agricultural activities. Artificial lakes and rivers bring water to the surface and breathe life into a barren landscape. They are symbols of the broader effort to transform Mars into a world capable of sustaining humanity and its ambitions. Each drop flowing through these features marks progress in the journey to reshape the red planet. Water recycling systems are essential for sustaining life on Mars, where every drop counts. These systems would ensure that water is reused efficiently, reducing the need to extract or import additional resources. By conserving water, they support long-term habitation and agricultural efforts. Closed-loop systems could be implemented in habitats to capture and purify wastewater from showers, sinks, and other uses. Advanced filtration and chemical treatments would restore the water to a drinkable state. This ensures a steady supply of clean water, even in remote or resource-limited environments. Agriculture on Mars would also benefit from water recycling systems. Excess water from irrigation could be collected and filtered for reuse. This process minimizes waste and supports the growth of crops in an arid environment. Recycling systems might incorporate biological methods, such as algae or plant-based filtration, to naturally purify water. These systems mimic Earth's ecosystems, using natural processes to remove contaminants. They are efficient and align with the goal of creating a self-sustaining environment. Energy-efficient technologies are crucial for operating water recycling systems on Mars. Solar power, in particular, offers a reliable source of energy to drive filtration and purification processes. This ensures that recycling systems remain operational under varying conditions. Mars's unique challenges, such as the presence of perchlorates in the soil, require specialized filtration systems. These technologies must remove harmful substances to ensure water is safe for consumption and use. Advanced materials and methods are key to overcoming these challenges. In addition to providing clean water, recycling systems reduce the environmental footprint of human activities. By minimizing water waste, they help maintain balance in the developing ecosystem. This is essential for the long-term success of terraforming efforts. Portable recycling units could be deployed to construction or exploration sites, allowing for immediate water reuse in field operations. These compact systems ensure that water remains accessible in all parts of the Martian environment. Flexibility and mobility enhance their value. Monitoring systems are an integral part of water recycling infrastructure. Sensors and automated controls ensure that purification processes operate efficiently and effectively. Real-time data helps detect and address issues before they become critical. Recycling systems could also play a role in atmospheric development. Water vapor produced during the recycling process might be vented to contribute to the growing atmosphere. This adds a secondary benefit to an already vital system. Scalability is a key consideration for water recycling on Mars. Systems must be designed to expand as populations and activities increase. Modular designs ensure that infrastructure can grow alongside settlements. Water recycling systems are more than a convenience. They are a necessity for survival on Mars. By maximizing the use of limited resources, these systems support every aspect of life and terraforming. They are a cornerstone of building a sustainable future on the red planet. Martian soil, or regolith, is rich in minerals but contains toxic compounds like perchlorates that are harmful to humans and plants. Decontaminating this soil is a critical step toward creating arable land for agriculture and sustainable ecosystems. Removing these toxins unlocks the potential for large-scale colonization. One method for decontamination involves using heat to break down perchlorates into less harmful components. High-temperature processes could be achieved using solar concentrators or specialized heaters. This approach efficiently targets the toxic compounds while preserving the soil structure. Another strategy is the introduction of engineered microbes capable of metabolizing perchlorates. These microorganisms would convert the harmful compounds into benign byproducts, naturally detoxifying the soil. This biological solution offers a scalable and sustainable approach. Washing the soil with water is another option, where perchlorates are dissolved and removed. This method requires recycling the water to minimize waste, making it an energy-intensive but effective solution. Combining it with other techniques could enhance its efficiency. Adding chemical treatments to neutralize toxins is also being explored. Certain compounds can bind to perchlorates, rendering them inert and safe for agricultural use. These treatments must be tailored to the specific composition of Martian soil. Decontamination efforts would likely begin near early settlement sites to prepare the ground for construction and farming. Targeting these areas ensures that resources are focused where they're needed most. Over time, the process could expand to cover larger regions. Monitoring systems would be essential for tracking the progress of soil decontamination. Sensors and automated platforms could measure toxin levels and ensure that treatments are working effectively. Real-time feedback enables adjustments to maximize success. Decontaminated soil could also support the growth of hardy plants, which would further improve its quality. These plants might contribute to soil aeration and the introduction of organic material. This process creates a foundation for more complex ecosystems. Challenges include ensuring that decontamination methods don't introduce new problems, such as altering the soil's physical properties or leaving harmful residues. Each technique must be thoroughly tested to avoid unintended consequences. Precision is key to long-term success. The energy demands for decontamination are significant, especially on a planetary scale. Solar or nuclear energy would be vital to power the required equipment and systems. Reliable energy sources ensure that the process can continue uninterrupted. Efforts to clean Martian soil also align with broader terraforming goals by preparing the planet for sustainable human activity. As the soil becomes more hospitable, it opens the door to agriculture, construction, and natural vegetation. These benefits ripple outward to support the entire mission. Decontaminating Martian soil transforms a barren landscape into a usable resource. It's a foundational step that enables life to take root and thrive on the planet. Every grain of clean soil brings us closer to turning Mars into a home. Martian soil lacks the organic nutrients needed to support plant life, making enrichment a key step in terraforming. Adding nutrients and fertilizers transforms the barren regolith into fertile ground, enabling agriculture and vegetation to thrive. This process builds the foundation for long-term sustainability. Transporting nutrient-rich fertilizers from Earth is one solution, especially in the early stages. These materials could jumpstart agriculture, while more sustainable methods are developed. Over time, the goal is to shift toward using Martian resources to produce nutrients locally. Bioengineered microbes could play a role in nutrient production, breaking down Martian minerals and releasing essential elements like nitrogen and phosphorus. These microorganisms could mimic the role of decomposers on Earth, enriching the soil naturally. This approach aligns with the goal of creating a self-sustaining ecosystem. Composting organic waste from human settlements could provide a renewable source of nutrients. Waste materials could be processed and returned to the soil, creating a closed-loop system. This not only improves soil quality but also reduces waste management challenges. The introduction of nitrogen is crucial for plant growth, but Mars's atmosphere lacks this vital element. Nitrogen could be extracted from imported resources or generated through industrial processes. Its incorporation into the soil is a priority for establishing agriculture. Phosphorus and potassium, essential components of fertilizers, might be sourced from Martian minerals. Mining operations could extract these elements, which would then be refined and distributed to agricultural zones. This reliance on local resources supports long-term scalability. Soil conditioning might also involve adding organic matter, such as algae or specially cultivated plants, to improve its structure and nutrient content. These organic materials help retain water and create a more stable environment for roots. Over time, they enhance the overall fertility of the soil. Hydroponic or aeroponic systems could be used to grow plants initially, allowing nutrient-rich runoff to be collected and reintegrated into the soil. These methods create an intermediate step, gradually transitioning to soil-based farming as conditions improve. This phased approach ensures consistent food production. Efforts to add nutrients must be carefully balanced to avoid over-fertilization or chemical imbalances. Monitoring systems would track nutrient levels and ensure they remain within optimal ranges. Precision application minimizes waste and maximizes the impact of each treatment. Energy-efficient production of fertilizers is essential for long-term success. Solar-powered chemical reactors or biological systems could provide a steady supply of nutrients without over-reliance on Earth. Developing these capabilities is a critical step in achieving self-sufficiency. Nutrient enrichment would likely begin near settlements, where agricultural activities are concentrated. As soil quality improves, these areas could expand outward, creating larger zones of fertile land. This gradual expansion supports both food security and ecosystem growth. Adding nutrients and fertilizers to Martian soil transforms it from an inhospitable substrate into a life-supporting resource. It bridges the gap between barren regolith and thriving ecosystems, enabling agriculture, vegetation, and biodiversity to flourish. This step is a cornerstone in the journey to make Mars a living planet. Introducing Earth microorganisms to Mars is a vital step in preparing the planet for life. Microbes play a critical role in breaking down minerals, cycling nutrients, and enriching soil. These small organisms can create the foundation for larger ecosystems over time. Certain microbes could be selected for their ability to thrive in harsh conditions similar to those on Mars. Extremophiles, which naturally survive in extreme environments on Earth, are prime candidates. These resilient organisms can begin transforming the Martian soil even in its current state. Nitrogen-fixing bacteria could be introduced to enrich the soil with nitrogen, an essential nutrient for plants. These bacteria convert atmospheric nitrogen into a form that plants can use, jump-starting the development of agricultural zones. Their presence helps bridge the gap between barren soil and fertile land. Other microorganisms might focus on breaking down toxic compounds like perchlorates, naturally decontaminating the soil. These microbes could be bioengineered to target specific toxins, ensuring the soil becomes safe for plants and humans. Their work lays the groundwork for future agricultural efforts. Photosynthetic microbes, such as cyanobacteria, could generate oxygen while contributing organic material to the soil. By converting sunlight and carbon dioxide into energy, these microbes help thicken the atmosphere and support the development of a breathable environment. They are a critical tool for creating habitability. Microbes that produce organic matter would also help improve soil structure, making it more capable of retaining water and supporting plant roots. These organisms act as natural fertilizers, enriching the soil over time. Their gradual contribution helps build a stable and sustainable ecosystem. The introduction of microbes must be carefully controlled to ensure they do not disrupt the Martian environment in unintended ways. Monitoring systems would track the growth and spread of microbial populations, ensuring they remain within safe and productive limits. This oversight is essential for long-term success. Microbial communities might initially be introduced in small, controlled test zones. These experiments would provide valuable data on how the organisms interact with the Martian environment. Successful trials could then be expanded to larger areas as part of the broader terraforming strategy. Energy and resources for supporting microbial growth, such as light, heat, and water, would be concentrated in these zones. Artificial environments could be created to give the microbes the best chance of survival and proliferation. Over time, these artificial supports could be phased out as the environment improves. As microbial colonies establish themselves, they could serve as the base for more complex life forms, including plants and eventually animals. Each layer of introduced life builds on the foundation created by microbes. This cascading effect gradually transforms Mars into a living planet. The diversity of Earth's microorganisms offers a wide range of possibilities for terraforming. By selecting and engineering the right combinations, we can address multiple challenges at once, from soil enrichment to atmospheric development. These small organisms hold the power to spark massive change. Introducing Earth microorganisms is more than a technical challenge. It's a moment of seeding life on another world. These microscopic pioneers represent the first step in creating ecosystems that will one day flourish across Mars, turning it from a barren desert into a thriving environment. Radiation is one of the most significant challenges when working with Martian soil. Without a protective magnetic field or thick atmosphere, Mars is constantly exposed to cosmic rays and solar radiation. This exposure can make the soil hazardous to humans, plants, and microorganisms. One concern is that high radiation levels might destroy organic material in the soil, preventing plants from taking root. Even microbes introduced to improve soil quality could struggle to survive in such harsh conditions. Finding ways to shield or treat the soil is essential for terraforming success. Radiation can also alter the chemical composition of the soil over time, potentially creating compounds that are toxic to life. Understanding these changes requires extensive testing and monitoring. This knowledge helps guide the development of effective countermeasures. Shielding the soil from radiation is one potential solution. Covering agricultural areas with protective domes or layers of Martian rock could block radiation and create safe zones for planting. These shelters would allow controlled environments for early stages of terraforming. Another approach involves treating the soil to neutralize or remove harmful effects caused by radiation. Adding specific chemicals or minerals might counteract radiation-induced toxicity. These treatments would ensure the soil remains viable for agricultural use. Bioengineered microbes could also play a role in repairing radiation damage. Some microorganisms are naturally resistant to radiation and might help restore the soil by breaking down harmful compounds. Their resilience makes them a valuable tool for addressing this challenge. Radiation-resistant plants and crops could be developed to thrive in Martian soil despite exposure. Genetic engineering might allow these plants to grow and even absorb some of the radiation, contributing to the gradual transformation of the environment. This innovation ensures food production can begin sooner. Energy-intensive solutions, such as heating the soil to remove certain radiation-induced compounds, might be necessary in highly contaminated areas. While demanding, these methods could prepare critical zones for settlement or farming. Targeted applications help focus resources effectively. Long-term exposure to radiation in the soil could also impact the structural integrity of buildings and infrastructure. Materials used for construction must be chosen to resist radiation damage, ensuring safety for future habitats. Addressing this issue protects both life and infrastructure. Monitoring systems are critical for understanding the extent of radiation exposure in the soil. Robotic sensors and probes could analyze radiation levels in real time, providing data to inform treatment strategies. Continuous monitoring ensures efforts remain adaptive and effective. Radiation's impact on soil also highlights the need for phased approaches to terraforming. Early efforts might focus on smaller, protected zones where radiation can be managed more easily. Expanding these areas over time allows gradual progress while minimizing risks. Addressing radiation in the soil is about more than overcoming a single challenge. It's about creating an environment where life can thrive safely and sustainably. Every solution brings us closer to transforming Mars into a world where ecosystems and civilizations can flourish. Sustainable agricultural practices are essential for supporting human life on Mars over the long term. With limited resources and an unforgiving environment, farming systems must be designed to maximize efficiency and minimize waste. These systems form the backbone of a self-sufficient colony. Hydroponic and aeroponic farming methods offer promising solutions for growing crops without soil. These systems use nutrient-rich water or mist to nourish plants, reducing the reliance on Martian soil. Their adaptability makes them ideal for early settlements and controlled environments. Recycling nutrients is key to maintaining a closed-loop agricultural system. Organic waste from crops and human activities can be composted or processed into fertilizers. This cycle ensures that essential nutrients are continuously replenished, supporting ongoing food production. Water use must also be carefully managed, with efficient irrigation systems that minimize evaporation and loss. Drip irrigation or moisture sensors can ensure that every drop of water reaches the roots of plants. These technologies are critical for farming in an arid environment. Crop selection plays a major role in developing sustainable agriculture. Hardy, fast-growing plants like algae, potatoes, or quinoa can thrive in challenging conditions and provide essential nutrients. These initial crops pave the way for more diverse agriculture as the environment improves. Genetically engineered crops could be tailored to grow in Mars' unique environment, including low temperatures and high radiation levels. These plants might also contribute to soil enrichment by fixing nitrogen or adding organic material. Their dual purpose supports both food production and ecological development. Greenhouses equipped with advanced climate control systems could provide the perfect environment for farming. These structures would protect crops from radiation and extreme temperatures while maintaining optimal humidity and light levels. Over time, they could expand as technology improves. Sustainable practices also include integrating livestock or aquaculture into agricultural systems. Fish, for example, could provide both protein and nutrient-rich water for hydroponic systems. This synergy enhances resource efficiency and expands dietary options. Energy-efficient lighting, such as LED systems tuned to specific wavelengths, could maximize plant growth while minimizing power consumption. Solar panels or nuclear energy would supply the power needed to run these systems, ensuring reliable operation in remote conditions. Automation and robotics can streamline farming processes, from planting and harvesting to monitoring soil and plant health. These technologies reduce the need for manual labor and improve precision, ensuring resources are used wisely. Automation is especially valuable in the early stages of colonization. As Martian soil becomes more viable through enrichment and decontamination, transitioning to soil-based agriculture could increase the scale of farming operations. Combining traditional farming methods with advanced technologies creates a hybrid approach that supports growing populations. Developing sustainable agricultural practices on Mars is about more than survival. It's about creating a thriving, resilient community. Each innovation and system contributes to a network of food production that grows alongside the colony, ensuring the red planet can truly support human life. Photosynthesis is the natural process that can transform Mars into a more habitable planet. By converting sunlight into energy, plants release oxygen and help create a breathable atmosphere. Introducing plants that thrive in harsh conditions is a key step in building a sustainable ecosystem. Bioengineered plants designed for Mars could withstand low temperatures, high radiation, and limited water. These plants would play a dual role, providing food and oxygen while contributing organic material to the soil. Their resilience makes them an invaluable tool for terraforming. Cyanobacteria and algae are some of the simplest organisms that could kickstart photosynthesis on Mars. These microorganisms are efficient at producing oxygen and can grow in environments where other plants might not survive. They are ideal for seeding early ecosystems. Fast-growing plants like mosses or grasses could be the next stage in establishing vegetation. These species would spread quickly, covering the Martian surface and stabilizing soil. Their presence would also support a natural progression toward more complex ecosystems. Bioengineered plants could be tailored to absorb and neutralize harmful compounds in Martian soil, such as perchlorates. This dual-purpose design ensures that plants contribute to both environmental detoxification and oxygen production. It's a practical solution to multiple challenges. Greenhouses equipped with artificial light could provide a controlled environment for photosynthetic organisms. These structures allow for precise management of temperature, light, and humidity, ensuring optimal growth. Over time, they could expand to accommodate a wider range of plants. As the atmosphere thickens and warms, photosynthetic plants could be gradually introduced to open environments. Hardy species would adapt to the evolving conditions, expanding their coverage across the planet. This gradual approach mirrors natural ecological succession. Genetic engineering might also enable plants to fix nitrogen from the atmosphere, enriching the soil with essential nutrients. These capabilities accelerate the transformation of Martian soil into a fertile medium for other forms of life. Each plant becomes a building block for the ecosystem. Energy from photosynthesis could help drive other biological processes, such as microbial activity in the soil. This synergy between plants and microorganisms creates a self-reinforcing cycle of growth and development. Over time, these interactions build a stable and thriving environment. The oxygen produced by plants would contribute to the gradual creation of a breathable atmosphere. Although this process could take centuries, it lays the groundwork for future human colonization. Every plant introduced to Mars brings the planet closer to habitability. Monitoring and adjusting plant populations would be essential to ensure they thrive under Martian conditions. Automated systems could track growth, health, and environmental impacts, providing data to guide decisions. This adaptive management ensures long-term success. Photosynthesis and bioengineered plants are the green spark that can bring life to Mars. These living systems have the potential to reshape the planet, creating air to breathe, soil to cultivate, and a future to grow into. They are the heart of terraforming efforts. Artificial oxygen production facilities are a vital component in creating a breathable atmosphere on Mars. These systems would supplement natural oxygen production from plants, accelerating the planet's transformation. Their reliability makes them an essential backup and enhancement to biological processes. Electrolysis is one method for producing oxygen, using electricity to split water into hydrogen and oxygen. Facilities equipped with electrolysis systems could process water extracted from subsurface ice or imported from asteroids. This technology provides a consistent and scalable source of oxygen. Another approach involves capturing and processing carbon dioxide from Mars's atmosphere. By using high-temperature chemical reactions, oxygen can be extracted while converting the remaining carbon into useful byproducts. This method utilizes Mars' abundant CO2 resources efficiently. Photocatalytic systems, powered by sunlight, could also contribute to oxygen production. These systems use specialized materials to break down carbon dioxide into oxygen and carbon under solar radiation. This energy-efficient method aligns well with Mars' reliance on solar power. Compact oxygen generators could be deployed near settlements to provide breathable air directly to habitats. These localized systems ensure a steady oxygen supply even during emergencies or equipment failures. They form a critical layer of redundancy and life support. Larger facilities might focus on producing oxygen for atmospheric enrichment, gradually increasing the breathable air available in open environments. These operations would require significant energy input, but could scale over time as the atmosphere develops. Their role grows with Mars' transformation. Nuclear-powered facilities offer another option, providing the consistent energy needed for oxygen production on a large scale. These reactors could operate independently of sunlight, making them reliable in all conditions. Their high output supports both settlement needs and planetary-scale efforts. Automated systems would play a key role in managing oxygen production facilities. Robotics and artificial intelligence could monitor efficiency, repair equipment, and optimize output. This automation reduces human labor and ensures continuous operation in Mars' harsh conditions. Waste heat generated by these facilities could also be repurposed for other terraforming efforts, such as warming the surrounding environment or melting ice. Integrating these processes improves overall efficiency and maximizes resource use. This interconnected approach benefits the broader mission. Oxygen storage and distribution systems would be essential for both immediate use and long-term planning. Pressurized tanks or underground reservoirs could store surplus oxygen, ensuring a buffer supply. Safe and efficient storage enhances the reliability of these facilities. Facility placement would need to consider proximity to water and energy sources, as well as the needs of nearby settlements. Strategic locations reduce transportation costs and ensure easy access to resources. Careful planning supports the success of these operations. Artificial oxygen production facilities are more than machines. They are a lifeline for humanity's future on Mars. By combining advanced technology with strategic deployment, these systems provide the air we need to breathe while shaping a habitable planet. They are the engines of transformation. Balancing oxygen levels within habitats on Mars is essential for ensuring the safety and health of its inhabitants. Too little oxygen could lead to suffocation, while too much could increase the risk of fires. Precise control systems are necessary to maintain the ideal balance for human life. Closed-loop life support systems would monitor and regulate oxygen levels in real time. These systems could integrate sensors that detect oxygen concentrations and automatically adjust production or release rates. This ensures a stable and breathable atmosphere within the habitat. Plants and algae grown inside habitats could provide a natural source of oxygen through photosynthesis. However, their oxygen output must be carefully calculated to match the needs of the population. Overproduction could create an oxygen-rich environment, which poses safety concerns. Artificial oxygen generators could supplement natural production, especially in high-demand situations. These systems would allow rapid adjustments to oxygen levels, providing flexibility during emergencies or periods of growth. Their reliability makes them a critical part of the infrastructure. Storage tanks could serve as reserves for oxygen, offering a buffer in case of system failures or unexpected needs. These tanks would allow excess oxygen to be safely stored and reintroduced as required. Having reserves adds a layer of security to the habitat's life support. Maintaining the right ratio of oxygen to other gases, such as nitrogen, is equally important. A balance that mimics Earth's atmosphere is necessary for human health and comfort. This mixture prevents issues like oxygen toxicity or decompression sickness. Habitat materials must also be designed to prevent oxygen leaks, ensuring the atmosphere remains stable over time. Advanced seals and barriers reduce the risk of loss while maintaining pressure. Preventing leaks minimizes waste and ensures resource efficiency. Monitoring and controlling oxygen levels become more complex as habitats grow larger or more interconnected. Centralized systems could coordinate oxygen management across multiple modules or sections, ensuring consistent conditions throughout the habitat. This scalability supports population expansion. Emergency protocols must be in place to handle scenarios where oxygen levels deviate from safe ranges. Automated alarms and manual overrides would allow quick responses to restore balance. These measures protect both the habitat and its residents from potential harm. Energy requirements for oxygen management must also be considered. Systems that produce, store, and regulate oxygen rely on consistent power supplies. Solar, nuclear, or hybrid energy sources would be critical to maintaining these operations without interruption. As habitats transition from sealed environments to more open systems, balancing oxygen levels will remain a priority. Even with partial exposure to the Martian atmosphere, life support systems must ensure breathable air within living spaces. This gradual adaptation aligns with long-term terraforming goals. Balancing oxygen levels in habitats is not just a technical challenge, it's about creating a safe and sustainable home for humans on Mars. Each system and safeguard contributes to a livable environment where people can thrive, laying the groundwork for a permanent presence on the red planet. Cyanobacteria play a crucial role in oxygen creation, offering a natural and efficient method to transform Mars's atmosphere. These microorganisms use sunlight to photosynthesize, converting carbon dioxide into oxygen. Their simplicity and resilience make them ideal for seeding a barren planet. Unlike larger plants, cyanobacteria require minimal resources to thrive. They can grow in extreme conditions, including those found on Mars, where water and nutrients are scarce. This adaptability allows them to contribute to oxygen production even in the early stages of terraforming. One advantage of cyanobacteria is their ability to grow rapidly and cover large areas. This scalability means they can quickly generate significant amounts of oxygen while laying the groundwork for more complex ecosystems. Their proliferation is a key step in building a breathable atmosphere. Cyanobacteria can also enrich the soil by adding organic material as they grow and die. This process helps prepare the Martian surface for the eventual introduction of plants and other life forms. Their dual role accelerates the ecological transformation of the planet. Introducing cyanobacteria to Mars might involve deploying bioreactors or growth chambers to protect them from initial harsh conditions. These controlled environments would provide light, water, and nutrients, allowing the bacteria to thrive and multiply. Over time, they could transition to outdoor environments as conditions improve. Cyanobacteria's ability to fix nitrogen adds another layer of value to their role. Nitrogen fixation enriches the soil, making it more suitable for agriculture and other vegetation. This process supports the broader goal of creating a self-sustaining ecosystem. Genetic engineering could enhance the natural capabilities of cyanobacteria, tailoring them to Mars' unique challenges. Modified strains might tolerate higher radiation levels or grow more efficiently in low-light conditions. These enhancements maximize their contribution to oxygen creation and soil development. Large-scale deployment of cyanobacteria could focus on areas with access to water, such as polar ice caps or artificial reservoirs. Concentrating growth in these regions ensures the bacteria have the resources they need to succeed. Strategic placement boosts the efficiency of their impact. The oxygen produced by cyanobacteria would gradually accumulate in the atmosphere, complementing artificial oxygen production facilities. Together, these systems work to create a balance between natural and engineered solutions. This synergy accelerates the overall terraforming process. Monitoring the growth and effects of cyanobacteria is critical to ensuring their introduction remains beneficial. Automated sensors and satellites could track their spread and measure oxygen levels, providing data to guide ongoing efforts. Oversight prevents potential imbalances or unintended consequences. Cyanobacteria also offer insights into the early stages of life on Earth, where similar organisms were responsible for creating an oxygen-rich atmosphere. Their role on Mars mirrors this ancient process, giving humanity a chance to replicate nature's success on another world. The role of cyanobacteria in oxygen creation is foundational to Mars's transformation. These tiny organisms pack an immense ecological punch, providing the first breath of life that will grow into a thriving and habitable planet. Their work is a testament to the power of biology in shaping the future. Long-term ecosystem stability is the ultimate goal of terraforming Mars, ensuring that the planet can sustain life without constant human intervention. Achieving this requires a delicate balance between biological, geological, and atmospheric systems. Each element must work in harmony to create a self-regulating environment. Establishing a diverse range of plant and microbial life is essential for stability. Biodiversity strengthens ecosystems by creating complex relationships between organisms, each contributing to nutrient cycling, soil health, and climate regulation. The more varied the ecosystem, the more resilient it becomes. Water availability is a cornerstone of any stable ecosystem. Rivers, lakes, and underground reservoirs must be maintained to support plant and animal life. A functioning water cycle that includes evaporation, condensation, and precipitation is critical for sustaining this balance. The soil must remain fertile and productive over time, which means ongoing enrichment and protection against erosion. Microbes, plants, and organic matter work together to keep the soil healthy, supporting agriculture and natural vegetation. Long-term fertility is key to maintaining food systems. Atmospheric stability is equally important, as changes in temperature, pressure, or composition could disrupt ecosystems. The atmosphere must remain dense enough to support life, while providing protection from radiation and extreme weather. Consistent monitoring ensures this balance is preserved. Ecosystems must also adapt to potential environmental fluctuations, such as temperature shifts or resource availability. Species that can tolerate a wide range of conditions are crucial for this flexibility. Their resilience helps maintain ecosystem function through change. Energy input, primarily from the sun, drives most ecological processes. Ensuring that plants and microorganisms can capture and use this energy efficiently supports the entire food chain. Solar-driven growth keeps ecosystems thriving and productive. Artificial interventions such as nutrient supplements or water redistribution might still be needed occasionally to correct imbalances. These systems would act as safeguards to ensure stability during unexpected challenges. Over time, reliance on these measures should diminish as the ecosystem matures. The introduction of animal life is a complex decision that must be carefully managed. Animals play vital roles in ecosystems, from pollination to nutrient cycling, but their needs must align with the environment's capacity to support them. Careful planning prevents strain on resources. Feedback loops within the ecosystem, such as plants producing oxygen that supports animals, which in turn enrich the soil, are essential for sustainability. These interconnected systems create a cycle of renewal, reducing the need for external input. Feedback loops are the backbone of stability. Monitoring and data collection are crucial for understanding how the ecosystem evolves over time. Satellite imaging, ground sensors, and biological sampling provide insights into health and balance. This data informs adjustments and ensures the ecosystem remains on track. Long-term ecosystem stability transforms Mars from a project into a living, breathing world. It's the culmination of every step in the terraforming process, creating a planet capable of sustaining life indefinitely. Stability is the foundation for a future where humanity and nature thrive together on Mars. Domed cities are the first step in establishing human presence on Mars, providing a controlled environment where life can thrive. These structures shield inhabitants from radiation, extreme temperatures, and the thin atmosphere. Their design makes them essential for survival during the early stages of colonization. Built with advanced materials, domes would create airtight enclosures capable of maintaining breathable air and stable pressure. Transparent sections allow natural sunlight to penetrate, supporting both human well-being and plant growth. This combination of protection and functionality ensures a livable space. Inside the domes, modular habitats would house residents, creating a compact and efficient layout. These units could be reconfigured as needed, adapting to changes in population or mission priorities. Flexibility in design makes domed cities scalable for growth. Agricultural zones within the domes would provide fresh food and oxygen, supporting self-sufficiency. Vertical farming systems maximize the use of limited space, ensuring that crops thrive in controlled conditions. These farms reduce dependence on Earth for supplies. Water recycling systems within the domes ensure that resources are used efficiently. Wastewater from daily activities is purified and reused, minimizing waste and supporting long-term sustainability. These systems are critical for conserving Mars' limited water supply. Energy for domed cities would come from solar panels, nuclear reactors, or a combination of both. Reliable power is essential for maintaining life support systems, lighting and heating. Ensuring uninterrupted energy supply is a priority for survival. The domes would also house research facilities, enabling scientists to study the Martian environment and test terraforming techniques. These labs would serve as hubs for innovation, driving the development of technologies needed to expand beyond the domes. Research accelerates the path to planetary transformation. To combat the isolation of living under domes, community spaces would be integrated into their design. Parks, recreation areas, and social hubs provide opportunities for relaxation and connection. These elements are vital for mental health and building a strong sense of community. Construction of domes would rely heavily on robotics and automated systems, reducing the risks associated with human labor in harsh conditions. Robots could assemble structures using materials sourced locally, such as Martian regolith. This approach minimizes reliance on Earth for building supplies. Over time, interconnected networks of domed cities could form the foundation of a larger Martian civilization. Transport systems between domes would facilitate movement and trade, creating a more cohesive society. These networks support collaboration and resource sharing. As terraforming progresses, the domes could transition into hybrid structures, partially open to the evolving Martian environment. This gradual integration ensures that cities adapt as conditions improve. The domes remain useful even as Mars becomes more habitable. Domed cities are not just shelters, they are the seeds of a new way of life. They provide the infrastructure, protection, and resources needed to establish humanity's foothold on Mars. Each dome is a step closer to transforming the red planet into a thriving home. Open environment terraforming aims to transform Mars into a planet where humans can live and work without the need for sealed habitats. This ambitious goal requires creating a breathable atmosphere, stabilizing temperatures, and introducing sustainable ecosystems. It represents the final phase in making Mars truly habitable. One primary objective is to thicken the atmosphere enough to support liquid water and protect against radiation. This involves releasing greenhouse gases, such as carbon dioxide and methane, to warm the planet and increase atmospheric pressure. A denser atmosphere is the cornerstone of open environments. Raising temperatures across Mars is another critical goal. By maintaining a stable and warmer climate, the planet can support plant growth and other biological processes. Warming also helps activate water cycles, a key component of a thriving environment. Establishing a breathable atmosphere means increasing oxygen levels over time. This could be achieved through a combination of photosynthetic plants, cyanobacteria, and artificial oxygen production facilities. Gradual oxygenation ensures a safe transition for future settlers. Creating water systems like rivers, lakes, and oceans is central to open environment terraforming. These features not only provide resources for life, but also help regulate the planet's temperature. Water is the lifeblood of any ecosystem, and its presence transforms barren landscapes. Open environments would require resilient vegetation capable of thriving in Martian soil. Hardy plants would stabilize the surface, prevent erosion, and contribute oxygen and organic material. Over time, these plants would pave the way for more complex ecosystems. Introducing animal life is a long-term goal that depends on the stability of the environment. Small insects and pollinators could be the first step, supporting plant diversity and food production. Gradually, larger species might be introduced as ecosystems evolve. Managing wind and dust storms is essential for ensuring the safety and sustainability of open environments. Stabilizing the surface with vegetation and controlling atmospheric dynamics would reduce the frequency and intensity of storms. This creates a more predictable and livable climate. Open environment terraforming also focuses on creating regions that mimic Earth-like conditions. Certain areas might be prioritized for development, becoming lush oases surrounded by harsher Martian terrain. These regions serve as starting points for expansion. Sustainability is at the heart of open environment goals. Systems must be self-regulating, with minimal need for human intervention. Balancing biological, geological, and atmospheric processes ensures that the planet remains habitable over the long term. Energy infrastructure would need to expand to support these open environments. Solar farms, geothermal energy, and other renewable sources would power systems for climate control, water distribution, and atmospheric management. Reliable energy is key to maintaining progress. Open environment terraforming is the culmination of efforts to reshape Mars. It transforms the planet from a hostile world into one where life can flourish naturally. Each milestone reached brings humanity closer to walking freely under the Martian sky. Balancing population and resources on Mars is crucial for the success of long-term colonization. A stable population ensures that resources are used efficiently without overwhelming the planet's capacity to provide. Careful planning is required to match growth with available supplies. Initial settlements will likely have strict limits on population size, determined by the availability of air, water, and food. These early communities must focus on self-sufficiency to reduce dependence on Earth. Controlled expansion allows resources to grow alongside the population. Water management is a key factor in maintaining balance. Recycling systems and sustainable extraction from ice deposits ensure that every drop is maximized. As more water sources are developed, the population can grow without straining this essential resource. Food production must scale with population growth, relying on efficient farming methods like hydroponics and aeroponics. These systems can produce high yields with minimal inputs, ensuring a consistent food supply. Over time, soil-based agriculture may further expand the capacity for food production. Energy demands increase as populations grow, making renewable energy systems critical. Solar, nuclear, and geothermal power must be scaled up to meet the needs of homes, farms, and industries. Reliable energy ensures that essential systems remain operational. Housing and infrastructure must expand thoughtfully to prevent overcrowding. Modular and scalable designs allow for flexibility as new settlers arrive. This approach ensures that living conditions remain safe and comfortable while avoiding resource strain. Transport systems between settlements play a role in balancing resources, allowing for efficient distribution of surplus supplies. Trade and collaboration between domed cities and open environments support a balanced economy. These networks ensure that no area becomes overburdened. The introduction of new settlers must consider the carrying capacity of the planet at each stage of its development. Quotas and careful selection processes ensure that population growth remains sustainable. Balancing human needs with planetary limits protects long-term viability. Ecosystem health is tied closely to population balance, as overuse of natural systems can destabilize the environment. Careful monitoring of water cycles, vegetation, and atmospheric conditions ensures that ecosystems continue to thrive alongside human populations. Harmony between humans and the environment is key. Education and training programs prepare settlers to contribute to the colony's resource management. Knowledge sharing ensures that every resident understands the importance of conservation and efficiency. A well-informed population helps maintain balance at every level. Technological advancements will play a significant role in improving resource efficiency, allowing the population to grow without depleting supplies. Innovations in recycling, energy use, and farming techniques increase the planet's carrying capacity over time. Progress is tied directly to technological development. Balancing population and resources on Mars is about creating a sustainable cycle of growth and renewal. By aligning expansion with the planet's capabilities, humanity ensures that life on Mars can flourish for generations to come. Every decision shapes the balance that sustains a thriving future. Zoning for agriculture, industry, and living is essential for organizing settlements on Mars and ensuring efficient use of space. Separating these activities prevents conflicts and promotes a well-functioning society. Clear zoning plans create the foundation for a thriving colony. Agricultural zones must be located near reliable water sources and energy infrastructure. These areas are dedicated to growing food, producing oxygen, and recycling waste. Proximity to habitats ensures that fresh resources are readily available. Industrial zones focus on manufacturing, resource extraction, and energy production. By placing these facilities away from living areas, the risks of noise, pollution, and accidents are minimized. These zones serve as hubs for building and maintaining the colony's infrastructure. Living zones prioritize safety, comfort, and community. Designed with modular habitats, these areas include homes, recreational spaces, and essential services. Their layout ensures that residents have access to everything they need while fostering a sense of belonging. Buffer zones between industrial and residential areas provide an additional layer of safety. These spaces could include greenbelts, parks, or research facilities, creating a physical and functional separation. This design ensures a balance between work and living environments. Transportation networks link all zones, allowing for the efficient movement of people and resources. Roads, rail systems, and pipelines ensure that materials flow smoothly between agriculture, industry, and living spaces. Connectivity is vital for maintaining productivity and collaboration. Zoning must adapt to the unique challenges of the Martian environment, including radiation exposure and limited resources. Underground or shielded facilities might be used for industrial activities, while greenhouses in agricultural zones are protected by domes. These adaptations make zoning practical for Mars. The placement of zones also considers future expansion, ensuring that growth can occur without disrupting existing systems. New agricultural fields, factories, or residential areas can be added in stages. This forward-thinking approach supports sustainable development. Mixed-use zones might emerge as the colony grows, combining elements of agriculture, industry, and living. These areas provide flexibility for smaller settlements or specific projects. Their adaptability ensures that all needs are met efficiently. Zoning plans must also account for environmental impact, ensuring that agricultural runoff or industrial byproducts do not harm other zones. Monitoring systems track these interactions, maintaining balance across the colony. Responsible zoning protects both people and the planet. Collaborative planning ensures that zoning meets the needs of diverse groups, from scientists to farmers to families. Input from residents shapes the layout of their community, creating a shared vision for life on Mars. This inclusivity strengthens the colony's foundation. Zoning for agriculture, industry, and living integrates function and harmony, creating a balanced society on Mars. Each zone supports the others, forming a network of interdependence that drives growth and sustainability. Thoughtful planning transforms the Martian landscape into a place where humanity can flourish. Transitioning from domes to open areas marks a pivotal moment in the terraforming of Mars. This shift represents humanity's ability to move beyond enclosed habitats and embrace a planet that supports life more naturally. It's a gradual process that combines scientific advancements with ecological development. The first step involves creating transitional zones, areas where domes are partially open to the evolving Martian atmosphere. These regions act as testing grounds to observe how plants, animals, and humans adapt to the new conditions. Success here informs the next stages of expansion. As the atmosphere thickens and temperatures stabilize, hardy vegetation can be introduced to areas surrounding the domes. These plants contribute to soil stabilization, oxygen production, and moisture retention, creating a foundation for more complex ecosystems. Their growth signals progress in transforming the environment. Water systems, such as artificial rivers and lakes, play a vital role in supporting life outside the domes. These features help regulate temperature and provide resources for plants and animals. Open water sources are a critical milestone in the transition to open areas. Gradually reducing reliance on sealed environments requires precise monitoring of oxygen levels, radiation, and temperature. Advanced sensors track these variables, ensuring that open areas remain safe for humans and other life forms. Adaptive systems allow for quick adjustments when needed. Temporary shelters or semi-enclosed structures might still be necessary during the transition. These hybrid spaces offer protection while allowing exposure to the new environment. They provide a balance between safety and adaptation as conditions improve. Introducing animals to open areas requires careful planning to ensure they have sufficient food, water, and shelter. Small, resilient species might be the first to venture beyond the domes, paving the way for more complex ecosystems. Each step is guided by the health and stability of the environment. Expanding human activities into open areas begins with agriculture, where crops are grown in fields rather than enclosed farms. These open agricultural zones demonstrate the progress of terraforming while reducing the need for intensive indoor systems. Success here supports further development. Infrastructure also transitions to open spaces with buildings and transportation systems designed to function under the new atmospheric conditions. Construction materials and methods evolve to meet the challenges of a partially terraformed Mars. These adaptations are key to creating lasting settlements. Communities begin to flourish as open areas grow, with parks, gardens, and public spaces integrating seamlessly into the Martian landscape. These environments encourage outdoor activities and strengthen the connection between people and their surroundings. A sense of normalcy emerges. As conditions continue to improve, domes may become relics of the past, repurposed for specific uses or preserved as historical landmarks. Their presence reminds settlers of the journey from enclosed survival to open exploration. Each dome tells the story of Mars' transformation. Transitioning from domes to open areas is the realization of humanity's vision for Mars. It's the moment when the planet becomes more than a project, evolving into a place where life thrives in harmony with its surroundings. Each open area represents a step closer to making Mars a second home. Managing Mars' thin atmosphere is one of the greatest challenges in terraforming. With atmospheric pressure less than 1% of Earth's, the planet cannot currently support liquid water or unprotected human life. Addressing this issue is essential for creating a habitable environment. The first step is increasing the atmosphere's density by releasing trapped gases from the soil and polar ice caps. Carbon dioxide, already present in large quantities, provides an immediate resource for thickening the air. Controlled release ensures steady progress without destabilizing the planet. Greenhouse gases such as methane and water vapor can enhance this process, helping to trap heat and warm the surface. Introducing these gases through industrial processes or biological systems accelerates atmospheric growth. This creates a feedback loop that supports further change. Artificial magnetic fields are critical for preventing the loss of gases to space. Without a protective shield, solar winds strip away the atmosphere over time. A magnetic field reduces this erosion, ensuring that progress in thickening the atmosphere is sustainable. Maintaining a balance between greenhouse gas levels and oxygen production is key. While carbon dioxide warms the planet, excess levels can be harmful. Gradually introducing photosynthetic organisms helps shift the composition toward a breathable mixture. Water vapor plays a dual role in managing the atmosphere, contributing to both temperature regulation and pressure. Melting polar ice caps or transporting water from other sources increases vapor levels. This moisture supports cloud formation and, eventually, precipitation. Dust storms are another factor to consider, as they can redistribute gases and affect atmospheric stability. Managing these storms involves stabilizing surface conditions and monitoring their impact on pressure levels. Preventing extreme weather improves the habitability of open areas. Energy production on Mars must account for the atmosphere's limitations, as solar panels and other systems operate differently under thin air. Adjustments to energy infrastructure ensure that essential systems, like atmospheric generators, function effectively. Reliable energy supports long-term stability. The transition from thin to thicker air must be carefully monitored to avoid unintended consequences. Sudden changes in pressure or composition could disrupt ecosystems or damage infrastructure. Gradual adjustments allow for controlled growth and adaptation. As the atmosphere thickens, it will begin to regulate itself more naturally, reducing the need for artificial intervention. Plants and other life forms contribute to the balance, creating a self-sustaining cycle. This natural regulation is a milestone in terraforming. Atmospheric sensors and satellites provide real-time data on pressure, temperature, and gas composition. These systems guide decision-making and ensure that progress stays on track. Continuous monitoring is essential for managing such a dynamic system. Managing Mars' thin atmosphere is a complex but necessary task. Every step in thickening and stabilizing the air brings the planet closer to supporting life, transforming it from a barren wasteland into a thriving world. Each breath of progress shapes the future of humanity on Mars. Meteorite and dust storm threats are constant challenges when living on Mars, where the lack of a thick atmosphere offers little protection. Meteorites, ranging from small particles to large rocks, regularly strike the planet's surface. Their impacts can damage habitats, disrupt infrastructure, and pose risks to human life. Shielding structures against meteorites requires innovative engineering. Protective barriers made from strong, lightweight materials can absorb the force of impacts, preventing damage. These systems must be designed to withstand frequent strikes, especially in early settlement phases. Robotic detection systems could be deployed to track incoming meteorites, providing early warnings for settlements. These systems would rely on satellites and sensors to predict the trajectory and size of objects. Alerts would allow settlers to take precautions or avoid areas at high risk. Dust storms, another frequent hazard, can obscure visibility and damage equipment with their abrasive particles. These storms can last for days or even weeks, creating a hostile environment for outdoor activities. Preparing for these storms is key to ensuring the safety of both people and technology. Dust storms also impact the atmosphere by redistributing fine particles, which could affect temperature regulation. They create localized cooling, potentially interfering with heating systems or agricultural zones. Understanding and predicting these storms helps mitigate their effects on the colony. Dust storms can also clog solar panels, reducing energy generation during critical times. Regular maintenance and cleaning systems are necessary to ensure that power remains consistent. In the long term, adapting energy infrastructure to these challenges will improve resilience. Agricultural zones, too, are vulnerable to dust storms, which can damage crops and disrupt photosynthesis. Protective domes or greenhouses help shield plants, ensuring that farming operations continue despite external conditions. Keeping plants safe from these environmental threats supports long-term food security. Developing self-cleaning systems or automated repairs for equipment damaged by dust is essential for maintaining the colony's functionality. These systems would help restore critical operations quickly, reducing downtime during or after a storm. Automation ensures that the settlement remains resilient. Meteorite impacts also pose a significant threat to communications and power infrastructure. Satellites, antennas, and cables could be damaged by even small meteors, leading to costly repairs and loss of connectivity. Redundant systems and shielded technologies are crucial for maintaining operational stability. The Martian surface is constantly bombarded with cosmic radiation, which can make meteorite impacts even more dangerous. These high-energy particles can change the composition of incoming rocks, potentially increasing their harmful effects. Shielding against both radiation and meteor impacts ensures the safety of settlers. Designing habitats to withstand meteorite impacts and dust storms requires collaboration between engineering and environmental sciences. By combining the best of both fields, we can create safe, functional spaces that protect against these threats. Every technological advancement contributes to a safer, more secure Mars. Meteorite and dust storm threats are reminders of Mars' hostile nature, but they also fuel innovation. By developing solutions to combat these dangers, humanity takes another step toward turning Mars into a habitable world. Each challenge is an opportunity to build a more resilient future. Technological failures on Mars pose significant risks to settlers and the success of terraforming efforts. From life support systems to communication networks, any breakdown in critical infrastructure could lead to severe consequences. Ensuring that backup systems are in place is vital to maintaining safety and functionality. One potential failure is the loss of power, which could disrupt essential systems like heating, oxygen production, and water filtration. Solar panels or nuclear reactors may fail due to dust storms, radiation damage, or mechanical issues. These vulnerabilities make it necessary to have redundant power sources that can take over if one system fails. Life support systems are another area where failure could have catastrophic effects. These systems regulate oxygen, pressure, and temperature within habitats. A malfunction in these areas could lead to life-threatening conditions, so regular maintenance and robust repair systems are crucial for preventing disaster. Communication failures could isolate Mars colonies from Earth or disrupt coordination between settlements. Loss of satellite links or damaged communication equipment could delay critical information or assistance. Building resilient communication networks with multiple channels of transmission reduces the risk of isolation. Water supply systems are critical for sustaining life on Mars, and failures in water extraction or filtration could quickly escalate into emergencies. Contamination, leaks, or failures in recycling systems could result in water shortages. Continuous monitoring and backup systems ensure a steady and clean supply of water. In agricultural systems, technology failures could result in crop loss or reduced food production. Automated farming systems, irrigation pumps, and nutrient delivery mechanisms must all function flawlessly. Any disruption in these systems could threaten food security, making them a high priority for maintenance. Robotic systems are integral to Mars exploration and terraforming, but they are also vulnerable to malfunction. These robots perform everything from habitat construction to resource extraction, and a failure in their operation could delay key projects. Ensuring they have fail-safes and the ability to self-repair is essential for maintaining progress. The Martian environment itself presents numerous challenges to technological systems, from extreme temperatures to intense radiation. These conditions can degrade materials and cause equipment to fail over time. Developing radiation-resistant and durable technology is key to ensuring long-term reliability. Transport systems between domed cities and open areas are also susceptible to failure. A breakdown in the transportation network could prevent essential supplies from reaching where they are needed. Robust maintenance protocols and alternative routes must be in place to avoid disruptions. Emergencies on Mars, such as equipment breakdowns or natural disasters, require quick and effective responses. Automation, coupled with trained human crews, can ensure rapid repairs and damage control. Having well-practiced procedures for dealing with failures is critical to minimizing risks. Terraforming efforts depend on continuous progress and coordination, and any technological setback could slow or halt these processes. It is important to build flexibility into the systems to adapt to unforeseen circumstances. Early detection of potential issues allows teams to act before they escalate into major failures. Addressing technological failures is a constant challenge on Mars, but each solution drives innovation. With the right strategies and resilient systems, Mars can be transformed into a world capable of supporting human life. Each failure overcome is a step forward in making the planet livable. The long-term viability of terraforming efforts on Mars hinges on the planet's ability to maintain the changes made over time. Initial successes in warming the atmosphere and introducing life must be sustained for centuries. This requires careful monitoring and management of both natural and artificial systems. One key challenge is the stability of the atmosphere. As gases are released to thicken the air, they must remain in place and not be lost to space. Ongoing strategies such as artificial magnetic fields and greenhouse gas production help ensure that the atmosphere stays intact and continues to evolve. Ecosystem development plays a crucial role in ensuring the long-term sustainability of the terraformed environment. Once ecosystems are established, they must function autonomously, with plants and microorganisms continuing to contribute to oxygen production and soil enrichment. Over time, these systems will evolve to support more complex life forms. Water is another critical resource that needs to be managed over the long term. As the planet warms and liquid water becomes more abundant, it must be carefully distributed and conserved. Reliable water systems will ensure that both ecosystems and human colonies have access to the resources they need to survive. As Mars' climate becomes more stable, the introduction of larger species such as animals will be necessary to create a balanced ecosystem. These species will play vital roles in pollination, nutrient cycling, and maintaining biodiversity. Their introduction must be gradual and carefully monitored to ensure the balance is maintained. The energy infrastructure on Mars must also be able to support long-term habitation. Renewable energy sources, such as solar and nuclear power, need to be scaled up as the population grows. Efficient energy storage and distribution systems will ensure that power demands are met without interruption. Resource extraction, including mining and material processing, will become increasingly important as the colony expands. Mars has abundant mineral resources that can support both industry and infrastructure. Ensuring sustainable resource management will prevent overexploitation and maintain the planet's ability to support life. Technological advancements will be necessary to address unforeseen challenges that arise as terraforming progresses. Continuous innovation in areas such as habitat construction, agricultural methods, and energy production will ensure that the colony remains resilient. Research and development will be crucial to adapting to changing conditions. Population growth on Mars must align with resource availability to prevent overpopulation and strain on systems. A carefully managed growth rate will ensure that the planet's infrastructure and ecosystems can support its inhabitants. Long-term planning will be essential to maintaining a healthy balance. The genetic engineering of plants, animals, and microorganisms will also play a role in ensuring long-term viability. These organisms must be designed to thrive in Martian conditions while contributing to the planet's ecological stability. Advances in biotechnology will help maintain and improve these systems over time. Over time, as the atmosphere thickens and ecosystems mature, Mars will gradually become more Earth-like. However, this transformation will take centuries, and there will be ongoing efforts required to preserve the progress made. Managing these long-term processes ensures that the terraforming effort remains viable and sustainable. Ultimately, the long-term success of terraforming efforts on Mars depends on the ability to adapt to challenges, manage resources effectively, and ensure the planet's ecological and atmospheric stability. Each phase of progress builds on the last, creating a foundation for future generations to thrive. Autonomous robotics will play a critical role in planetary engineering on Mars, handling tasks that are too dangerous, tedious, or time-consuming for humans. These robots will be equipped with advanced sensors, artificial intelligence, and specialized tools to perform everything from construction to environmental monitoring. Their ability to operate independently ensures that the terraforming process continues efficiently. Robots designed for excavation and resource extraction will be essential for mining Mars' abundant minerals and ice deposits. These machines can work continuously, excavating materials to be used for building habitats, energy production, and atmospheric generation. Their efficiency speeds up the initial stages of terraforming, reducing the need for human labor in harsh environments. Drones and rovers will be deployed to survey and map the Martian surface, identifying areas that are most suitable for agricultural development or habitation. By collecting real-time data, they help make informed decisions about where to direct resources. These autonomous vehicles ensure that exploration and development are carried out with precision. Robots will also be essential in building the infrastructure needed for a growing Martian colony. From assembling habitats and greenhouses to laying down power grids and communication networks, autonomous construction machines will reduce the time required for large-scale projects. Their ability to perform tasks remotely or under extreme conditions makes them indispensable. In the early stages of terraforming, autonomous robots will be responsible for implementing atmospheric management systems, such as releasing greenhouse gases and monitoring their spread. These robots will be able to perform delicate tasks, ensuring that the process of warming the planet and thickening its atmosphere is carried out safely and efficiently. Robotic systems will also help in maintaining critical systems, such as solar panels, water filtration units, and energy production facilities. Regular maintenance by autonomous machines ensures that equipment remains functional over time, without requiring frequent human intervention. This increases the reliability of long-term terraforming infrastructure. As the environment on Mars becomes more stable, robots will take on roles in ecosystem management, including planting, cultivating, and monitoring plant life. These systems will ensure that the process of introducing vegetation is consistent, adjusting growth conditions in real time. By managing ecological balance, autonomous robots ensure the health of the planet's developing ecosystems. Robotics will also be used for waste management, efficiently recycling and processing materials to minimize the use of resources. Robots will collect, sort, and repurpose organic and industrial waste, contributing to a circular economy on Mars. This technology ensures that waste does not become a burden on the ecosystem or the colony's infrastructure. AI-driven robots will also play a key role in conducting scientific research, gathering data on the planet's changing conditions. From analyzing soil composition to studying atmospheric changes, these autonomous systems will provide valuable insights into the effectiveness of terraforming efforts. Their continuous operation allows for consistent, up-to-date knowledge of Mars's transformation. Advanced robotic systems will also be capable of adapting to unforeseen challenges, whether they involve technical failures, environmental changes, or unanticipated obstacles. With the ability to modify their actions based on real-time data, these robots ensure the success of the terraforming project despite any setbacks. Their flexibility and intelligence make them ideal for this complex and ever-changing task. The integration of autonomous robotics will reduce the risks faced by human settlers, allowing them to focus on tasks that require human ingenuity and oversight. With robots performing the majority of the heavy lifting, settlers can dedicate more time to research, community building, and long-term planning. This division of labor optimizes both human and robotic contributions to the colony's success. As Mars continues to evolve, autonomous robotics will become increasingly sophisticated, expanding their capabilities and range of tasks. From assisting with large-scale infrastructure projects to supporting the development of thriving ecosystems, robots are the backbone of planetary engineering. Their role in the terraforming of Mars is essential for turning the red planet into a home for humanity. Advanced mining and resource extraction are essential for supporting the infrastructure and sustainability of Mars' growing colony. Mars is rich in minerals, water ice, and other valuable resources that can be harnessed to build habitats, generate energy, and sustain life. Efficient extraction systems will be crucial in meeting the needs of settlers while minimizing environmental impact. Automated mining robots will play a central role in extracting resources from the Martian surface and subsurface. These machines can dig, drill, and extract materials with precision, reducing the need for manual labor in harsh conditions. Their ability to operate independently in remote locations accelerates resource collection, which is key to terraforming efforts. One of the most critical resources for terraforming is water, and Mars' subsurface ice deposits hold vast potential. Advanced drilling systems capable of reaching these deep ice layers will provide the water necessary for human life, agriculture, and atmospheric generation. These systems will need to be robust enough to function in Mars' cold and challenging environment. In addition to water, Mars is rich in metals such as iron, aluminum, and magnesium, which will be needed for building infrastructure and equipment. High-tech mining tools that can process these raw materials quickly and efficiently are essential for supporting the rapid expansion of the colony. These materials will also play a vital role in the construction of new habitats and energy systems. The extraction of carbon dioxide from the atmosphere is another important task for resource systems. Mars's thin atmosphere contains large amounts of CO2, which can be harvested for greenhouse gas production to thicken the atmosphere. Specialized systems will extract this gas and process it, contributing to the warming of the planet and making it more habitable. Mining and resource extraction operations will need to be carefully managed to avoid overexploitation of Mars's natural resources. Sustainable mining practices, including efficient recycling and minimal disruption to the environment, will ensure that these resources remain available for future generations. Long-term planning will be key to preventing depletion and maintaining a balanced ecosystem. Energy generation is another key consideration when extracting resources. Mining operations require a significant amount of power, which can be supplied by solar energy or nuclear reactors. Reliable and efficient energy systems will power mining robots, processing plants, and other infrastructure while minimizing the colony's dependence on Earth. Processing raw materials is another step in the resource extraction process. Once mined, these materials must be refined and converted into usable forms, such as building materials or fuel. Advanced chemical and mechanical processing systems will turn Mars' raw resources into the building blocks of the colony's growth. The mining process on Mars will also require the development of advanced tools and machinery capable of handling the planet's unique geological conditions. Mars's surface and subsurface are very different from Earth's, requiring specialized equipment that can cope with the challenges posed by the harsh environment. This includes machinery capable of dealing with dust storms, low temperatures, and low atmospheric pressure. Automation and AI will allow mining operations to be run efficiently with minimal human oversight. Robotic systems can operate in high-risk areas, conducting repairs, maintenance, and extraction tasks autonomously. This reduces the risks associated with manual labor and ensures that operations continue uninterrupted. One of the advantages of mining on Mars is the potential to use local resources for construction and manufacturing. Mars' abundant regolith can be processed into building materials such as concrete, which will be essential for constructing habitats and other infrastructure. Resource extraction reduces the need for costly imports from Earth, making the colony more self-sufficient. Mining operations on Mars are not just about extracting resources. They are about laying the foundation for the colony's future. By providing essential materials, water, and energy, mining systems support the ongoing development of a sustainable, thriving Martian settlement. The success of these operations directly influences the long-term viability of human life on Mars. 3D printing technology will play a pivotal role in constructing infrastructure on Mars, offering a fast and efficient way to build essential structures. By using local materials, such as Martian regolith, 3D printers can create habitats, roads, and even tools. This method reduces reliance on Earth-based imports, making it a sustainable solution for long-term development. The ability to print large-scale structures directly on Mars will greatly accelerate the construction of habitats. These 3D printers can layer materials to create walls, foundations, and roofs in a matter of days or weeks, depending on the complexity of the design. This speed is crucial for quickly establishing safe environments for settlers. 3D printing can also be used for manufacturing essential items, from machinery parts to medical tools. Instead of relying on shipping, settlers can simply print what they need on site. This flexibility supports both the immediate needs of the colony and its long-term growth by providing a local, reliable supply of materials. The versatility of 3D printing allows for the creation of customized designs tailored to Mars' unique environmental conditions. Whether it's creating insulation to withstand extreme temperatures or building structures to resist radiation, 3D printers can be programmed to meet specific needs. This adaptability ensures that infrastructure can evolve with the colony. A key advantage of 3D printing on Mars is its ability to minimize waste. The precise layering of materials means that only the necessary amount is used for each print, significantly reducing resource consumption. This waste reduction is vital for conserving the limited resources available on the planet. By incorporating 3D printing into construction processes, settlements can be built with greater architectural complexity. Structures can be printed with built-in features, such as integrated piping, wiring, and insulation, eliminating the need for additional steps. This streamlines construction and enhances the efficiency of each project. 3D printers can also be used for building repair and maintenance. If a part of a habitat or infrastructure becomes damaged, a replacement part can be printed locally, reducing downtime and preventing the need for expensive transport from Earth. This self-sufficiency improves the colony's resilience in the face of unforeseen challenges. In addition to traditional building materials, 3D printers can work with a variety of unconventional materials. For example, they could utilize recycled waste products or biological materials to create sustainable construction components. This opens up new possibilities for resource use, contributing to a circular economy on Mars. The use of 3D printing extends beyond buildings and infrastructure to include scientific research facilities, laboratories, and manufacturing hubs. With the right designs and materials, almost any kind of structure can be printed to support the growing needs of the Martian colony. This capability allows for scalable growth as the settlement expands. Robots equipped with 3D printing technology will be able to operate in hazardous environments, reducing the risk to human settlers. These autonomous systems can build in areas that might otherwise be too dangerous, such as near high radiation zones or unstable terrains. This capability ensures that construction continues even in the most challenging locations. By integrating 3D printing into the Martian construction process, settlers gain an essential tool for both emergency response and everyday needs. Whether it's creating temporary shelters, expanding residential areas, or building research centers, 3D printing enables rapid and efficient growth. It is one of the cornerstones of developing a sustainable colony on Mars. As 3D printing technology advances, so too will its ability to handle more complex construction tasks. From multi-story buildings to intricate scientific equipment, the possibilities are vast. By harnessing this innovative technology, humanity can create a thriving, self-sufficient settlement on the surface of Mars. Energy is the lifeblood of any Martian colony, powering everything from life support systems to industrial machinery. Given the planet's harsh environment, reliable and efficient energy sources are essential. Solar and nuclear power will play central roles in providing the energy needed to sustain life and support terraforming efforts. Solar energy is one of the most accessible and effective sources on Mars. The planet receives a steady stream of sunlight, and solar panels can be used to capture this energy. By placing large solar arrays in strategic locations, settlers can generate a significant portion of their energy needs. Nuclear energy offers a more consistent and powerful energy source, particularly during Mars' long nights and dust storms. Nuclear reactors provide continuous power, which is essential for maintaining critical infrastructure and operations. Their high energy output supports everything from heating systems to atmospheric control devices. Solar and nuclear power will complement each other, with solar panels providing daytime energy and nuclear reactors ensuring a steady supply during the night or cloudy periods. This hybrid energy system allows for greater flexibility and stability, ensuring that power is always available when needed. Geothermal energy is another potential resource for Mars, particularly in regions with volcanic activity. The heat from the planet's interior could be harnessed to generate electricity, offering a renewable and sustainable power source. This could supplement solar and nuclear energy, diversifying the colony's energy mix. Wind energy could also be harnessed using turbines designed to operate in Mars' thin atmosphere. While winds are less powerful than on Earth, large turbines could still generate useful amounts of power in specific locations. Wind energy could provide an additional layer of energy security for Martian colonies. Energy storage systems will be essential for ensuring that power remains available during periods of low production, such as at night or during dust storms. Advanced batteries and energy storage devices will store excess energy generated during the day for use when needed. These systems ensure that the colony remains operational 24/7. Hydrogen fuel cells offer another viable energy solution, especially for mobile applications such as vehicles and spacecraft. By splitting water into hydrogen and oxygen, these cells can provide a clean and efficient source of power. Hydrogen fuel cells complement other energy systems by offering portability and flexibility. Mars also has potential for harnessing its abundant resources for energy production. Extracting carbon dioxide from the atmosphere and using it in fuel production could provide a self-sustaining energy cycle. This process would reduce reliance on Earth for materials while supporting both energy production and atmospheric thickening. Energy production on Mars must be both sustainable and efficient to support a growing colony. As the settlement expands, the demand for power will increase, requiring a scalable and reliable infrastructure. Developing these energy sources in tandem with the colony's growth ensures long-term viability. Energy efficiency is key to minimizing waste and maximizing available resources. As the colony develops, new technologies will be implemented to reduce energy consumption, from smart grids to more efficient power systems. These advancements allow the colony to thrive while minimizing its environmental impact. With a combination of solar, nuclear, and other energy sources, Mars can become a self-sustaining world where human life can flourish. Each energy source plays a unique role in powering the colony, and together they form a robust system that meets the needs of a growing population. By diversifying energy options, settlers can ensure their survival and success on the Red Planet. Transportation systems on Mars will be essential for connecting different parts of the colony and facilitating the movement of people and goods. With a vast and rugged landscape, these systems must be efficient, reliable, and adaptable to the unique challenges of the Martian environment. Developing robust transportation infrastructure is a critical step in building a sustainable settlement. Rovers and specialized vehicles will be the primary means of surface transport, allowing settlers to travel across the planet's terrain. These vehicles will be equipped with advanced wheels or tracks to handle the rocky, uneven ground. Their designs will focus on durability and efficiency, ensuring they can withstand harsh conditions. For longer distances, Mars will need a system of transport hubs and roads. These paved or reinforced paths will connect settlements, mining sites, and other critical infrastructure. Establishing these routes early on will create a network that supports trade, travel, and resource distribution. Transporting materials from mining sites to processing centers and settlements is another crucial aspect of Martian transportation. Conveyor belts, automated trucks, and robotic systems will move resources efficiently across the planet. These systems must be capable of operating continuously, even in Mars' extreme conditions. In addition to ground transportation, Mars will need a reliable aerial transport system. Drones and airships could be used to transport goods and personnel between settlements or to hard-to-reach areas. These vehicles will take advantage of Mars' thinner atmosphere, with specialized designs for low lift and high efficiency. Spaceports will be necessary for launching and receiving spacecraft traveling between Mars and Earth. These facilities will be equipped with docking stations, fueling systems, and other infrastructure needed to maintain interplanetary transportation. Spaceports will serve as critical hubs for long-distance travel and resource exchange. The transportation system will need to include rapid transit options within settlements. Maglev trains or electric vehicles could be used to move people quickly between different parts of a colony, reducing travel time and increasing efficiency. These systems must be integrated into the larger transportation network to ensure smooth operations. Habitat mobility is another consideration for Mars, with settlers potentially needing to relocate or move habitats as the colony grows. Mobile habitats or modular living units will be designed to be transported by specialized vehicles. These units will provide flexible, scalable living spaces that adapt to the changing needs of the colony. Energy-efficient transport systems will be essential for sustainability on Mars. Solar power, battery storage, and even hydrogen fuel cells could power ground vehicles, reducing reliance on Earth-based fuel. These green technologies will ensure that transportation continues without damaging the Martian environment. Safety is a top priority in all transportation systems. Given Mars' challenging conditions, vehicles will be equipped with advanced navigation systems, collision avoidance technology, and emergency protocols. These systems will ensure that settlers can travel safely, even in the face of unexpected challenges. Automated transportation will also play a major role in Mars's future. Robots and drones can be used for deliveries, equipment transportation, and other tasks that reduce human exposure to hazardous environments. By relying on automation, the settlement becomes more resilient and able to handle unforeseen disruptions. Mars's transportation systems will evolve as the colony grows, with each new system expanding on the last. From rover expeditions to the construction of spaceports, transportation infrastructure will be the backbone of the settlement's development. Each advancement brings humanity closer to establishing a thriving and connected presence on the Red Planet. The involvement of international space agencies will be critical in the successful colonization and terraforming of Mars. Collaboration between organizations such as NASA, ESA, Roscosmos, and private companies will bring together a wealth of expertise, resources, and technologies. By working together, These entities can share the financial and technical burdens of such a massive endeavor. Global partnerships will allow for the pooling of resources, creating more efficient and cost-effective solutions. With multiple countries contributing to research, technology development and infrastructure, the efforts to establish a Martian colony will be faster and more comprehensive. This teamwork ensures that all aspects of the project, from transport to life support, are tackled from a wide range of perspectives. International space agencies can also provide crucial support in terms of expertise. NASA's long history with Mars exploration, ESA's advanced satellite capabilities, and Roscosmos's expertise in human spaceflight and station maintenance will all play vital roles. Each organization's strengths complement one another, creating a synergy that makes Mars colonization possible. Involving space agencies from different countries ensures that the project benefits from diverse technological innovations. Each nation brings unique solutions to the table, from propulsion technology to habitat designs. This variety leads to breakthroughs and fosters a spirit of innovation that drives progress forward. Collaboration extends beyond technology and expertise. It also involves sharing the risks and rewards of such a monumental project. With international involvement, the political and financial risks are spread out, making it more feasible for individual nations to contribute. The global nature of the project also ensures that the benefits of colonizing Mars are shared by many. International collaboration will be essential in the establishment of Mars-based infrastructure, including spaceports, communication systems, and research stations. By combining efforts, these agencies can establish a reliable transportation network between Earth and Mars, facilitating the exchange of resources, scientific knowledge, and personnel. Governments around the world can use their space agencies to support research and development focused on the long-term sustainability of Mars. Funding for ongoing terraforming efforts, such as atmospheric modification or resource extraction, will be more sustainable when shared. Long-term commitments from global space agencies ensure that projects remain funded and operational. Through international agreements, laws and regulations governing the use of Martian resources can be established. These frameworks will ensure that the exploitation of Mars's resources is done responsibly, without harm to the environment or potential conflicts between nations. By creating a shared understanding, space agencies can work toward peaceful and equitable exploration. Human resources from various countries can be brought together to form a truly global team working on Mars. Collaboration among scientists, engineers, and astronauts from different cultures creates a strong foundation for problem-solving. This diversity fosters creativity, bringing new ideas and perspectives to the table. International agencies can also play a crucial role in maintaining long-term peace and cooperation. With Mars being a shared space, it's important to ensure that all countries have equal access and opportunities. Diplomatic efforts by these agencies will prevent territorial disputes and promote peaceful collaboration. The combination of government space agencies and private companies will further strengthen the global effort. Partnerships between organizations like SpaceX and national space agencies will allow for the rapid development of spacecraft and habitats. These collaborations allow for faster progress and the scaling of infrastructure projects. Lastly, the involvement of international space agencies ensures that Mars colonization remains a shared goal of humanity. It's not just one nation's project, it's a unified effort to ensure the survival and advancement of civilization. This collective endeavor makes Mars colonization a symbol of what humanity can achieve when united. Private space companies will play a pivotal role in the future of Mars colonization by bringing innovation, efficiency, and a competitive edge to the table. These companies, such as SpaceX, Blue Origin, and others, are accelerating space exploration with cutting-edge technology and ambitious goals. Their involvement complements the work of national space agencies, creating a dynamic, multifaceted approach to the challenges of colonizing Mars. The development of reusable spacecraft by private companies has significantly reduced the cost of space travel, making missions to Mars more affordable. Reusable rockets lower the cost per launch, enabling more frequent and cost-effective trips between Earth and Mars. This breakthrough opens up new possibilities for transporting materials, equipment, and people to the Red Planet. Private companies also bring agility and flexibility to Mars exploration. Unlike government agencies, these companies can respond quickly to emerging technologies and market demands. Their ability to innovate rapidly means that new solutions for energy production, habitat construction, and life support can be implemented faster than ever before. In addition to developing spacecraft, private companies are also investing in new technologies to support the infrastructure needed for Mars colonization. For example, SpaceX's plans to build the Starship spacecraft include features designed specifically for interplanetary travel. This includes the ability to carry large payloads, making it possible to transport the vast amount of equipment required for colonization. Private companies are also actively working on developing systems for in situ resource utilization, ISRU, which is key to making Mars habitable. By developing technology to extract water, oxygen, and fuel from the Martian environment, these companies reduce the need for resources from Earth. This approach is essential for building sustainable colonies that can thrive independently. The role of private companies also extends to habitat design and construction. Many private entities are working on 3D printing technologies that can produce housing and other structures directly on Mars using local resources. This capability will be vital in establishing a permanent human presence, allowing for rapid expansion as the colony grows. Now, private companies are playing a major part in the development of space tourism and commercial activities on Mars. As the technology to reach Mars becomes more accessible, these companies will offer services to civilians, researchers, and tourists alike. This expansion of the space economy will help fund further Mars exploration and infrastructure development. In addition to technological advancements, private companies bring a new source of funding to Mars projects. With their ability to attract private investment, they can supplement government funding and drive large-scale projects. This financial contribution accelerates the pace of colonization and ensures the long-term viability of the settlement. Private companies also contribute to the workforce for Mars exploration. By offering training programs, research opportunities, and job creation in the space industry, they help cultivate a new generation of experts in fields like aerospace engineering, robotics, and space medicine. This growing workforce supports the continued development and sustainability of Mars missions. The competition between private space companies pushes all players to innovate and improve. The desire to be the first to establish a permanent presence on Mars or to offer the most efficient transportation systems drives progress in technology. This competitive spirit accelerates the entire colonization effort, leading to faster and more effective solutions. With the support of private companies, Mars colonization becomes not just a government-driven project, but a global, multifaceted effort. The expertise, funding, and innovative technologies provided by these companies complement the broader goals of planetary exploration. As a result, the involvement of the private sector is indispensable to the success of humanity's future on Mars. Private space companies are the key to unlocking the full potential of Mars colonization. Their ability to push boundaries, innovate, and drive costs down will help make the dream of a self-sustaining Martian colony a reality. Together with government agencies, they will shape the future of humanity on the Red Planet. Creating Martian laws and policies will be essential for establishing a stable and functioning society on Mars. As humanity expands its presence on the Red Planet, frameworks need to be put in place to govern everything from resource management to individual rights. These laws will ensure that the colony operates efficiently and harmoniously. One of the first issues to address is the ownership and use of Martian resources. Legal agreements and policies must be created to ensure fair distribution and prevent conflicts over land, water, and minerals. This includes setting up guidelines for in situ resource utilization and determining who controls and benefits from Martian resources. Establishing environmental protection laws will be crucial to preserving the delicate Martian ecosystem. As terraforming efforts progress, it's important to ensure that human activities do not cause irreversible damage to the planet. Creating regulations for waste management, pollution, and conservation will maintain balance as the environment evolves. Martian laws will also need to address the rights and responsibilities of settlers. This includes everything from labor rights to land ownership, ensuring that settlers' interests are protected. As the population grows, legal frameworks will have to adapt to reflect the needs and demands of a diverse community. International agreements will play a key role in shaping Martian policies, especially in relation to Earth-based organizations and nations. Global treaties will be needed to manage interplanetary travel, trade, and cooperation. These international laws will ensure that Mars colonization remains peaceful and collaborative. As the colony becomes more established, Martian citizens will likely seek local governance. Policies must be created to determine how leaders are chosen, how laws are enforced, and how the voice of the settlers is heard. Establishing systems for self-governance will be vital for the growth of the colony and its ability to make independent decisions. Economic regulations will also need to be addressed, from currency systems to taxation. Policies must be in place to ensure that economic activities are fair, transparent, and sustainable. This includes managing trade between Mars and Earth, as well as within the Martian settlements themselves. Safety and security will be key concerns as the population grows, requiring laws that address everything from criminal justice to defense. Mars will need to establish law enforcement agencies and security protocols to maintain order. These systems will help prevent and address potential conflicts or threats to the colony's stability. Ethical issues related to the use of technology, especially in relation to genetic engineering or artificial intelligence, will need to be considered. Martian laws will have to define the acceptable uses of these technologies and ensure that they are used responsibly. Establishing ethical boundaries will be essential for ensuring the safety and well-being of the population. Martian immigration policies will also need to be established to manage population growth and ensure that settlers are equipped to live on the planet. Guidelines for who can migrate to Mars and under what conditions will help ensure that the colony remains sustainable. This may involve health checks, skill requirements, and resource limitations. As Martian society becomes more diverse, cultural policies will need to be developed to promote inclusivity and equality. Legal protections for different cultural, religious, and social groups will be necessary to ensure a harmonious society. These policies will reflect the values of fairness and respect for all settlers. Finally, Martian laws will need to evolve as the colony grows and changes. Continuous input from settlers, scientists, and policymakers will shape the legal framework as new challenges and opportunities arise. Creating adaptable, forward-thinking policies will ensure that Mars remains a place where life can thrive and society can flourish. Ethical considerations will be fundamental in the governance of Mars as humanity begins to settle and transform the planet. As the first permanent human presence on another world, the decisions made will set a precedent for future generations. These decisions must take into account the well-being of settlers, the preservation of the Martian environment, and the fair use of resources. The rights of the settlers will be a primary ethical concern. Determining who has a voice in the decision-making processes and how their rights are protected in an entirely new environment is crucial. Ensuring that all individuals have equal access to opportunities and protections will be essential in creating a just society. The potential impact of human activities on Mars' fragile environment raises significant ethical questions. Terraforming, resource extraction, and the introduction of Earth-based organisms could disrupt the natural state of the planet. These actions must be weighed against the benefits they bring to human survival, ensuring that we do not cause irreversible harm. Another key ethical issue will be the distribution of resources. Mars has limited resources, and decisions must be made about who controls them and how they are shared. Fair and equitable policies will be needed to prevent exploitation and ensure that no individual or group monopolizes the essential materials needed for survival. The role of artificial intelligence and automation in Mars governance will also raise ethical concerns. As robotic systems take on more responsibilities, including decision-making, it is essential to ensure that these technologies are used responsibly and ethically. The impact of AI on jobs, privacy, and autonomy must be carefully considered. The possibility of introducing genetically modified organisms or altering the biology of living beings on Mars also presents an ethical dilemma. Modifying the Martian environment to support life could have unintended consequences. Decisions around genetic manipulation, both for plants and humans, must be guided by ethical principles that prioritize safety and long-term health. Ethical questions will also arise around the governance structure itself. Should Mars be governed as an extension of Earth's laws, or should settlers develop their own legal and political systems? The principles of democracy, self-governance, and representation will need to be balanced with practical considerations about governance in a harsh and isolated environment. Mars colonization will raise issues of consent, particularly regarding who is sent to the planet. Volunteers will likely be the first settlers, but future generations may be born on Mars, inheriting a society that they had no part in creating. Ethical frameworks must address these concerns and ensure that all residents, regardless of their origins, have a voice in governance. With the development of advanced technologies, the ethical use of such technologies becomes even more crucial. From autonomous robots to potential nuclear energy production, the societal impact of these technologies must be fully understood. The risks of misuse or harm must be carefully managed with appropriate regulations and oversight. The question of inequality will also arise on Mars, as some individuals and groups may have more access to resources and opportunities than others. These disparities could affect the quality of life for different segments of the population. Policies must be put in place to address social and economic inequalities, ensuring that everyone has access to basic needs. Mars's political and legal systems will be tested by ethical dilemmas that humanity has never faced before. Decisions made on Earth will affect the lives of future generations on Mars, and vice versa. Transparent, accountable governance will be key in ensuring that Mars development is fair, sustainable, and just. Lastly, the ethical responsibility to future Martian generations will shape the long-term decisions made during the colonization process. The decisions made now will impact the social, environmental, and political landscape for centuries. As the first settlers, we must act with foresight and care, understanding that the choices we make today will echo through generations to come. Managing conflicts on Mars will require thoughtful approaches, as the challenges of living on the red planet are compounded by isolation and limited resources. Settlers must learn to collaborate, as conflicts arising from scarcity or cultural differences could jeopardize the success of the colony. Clear systems for dispute resolution will be essential for maintaining peace and cooperation. The first step in conflict management is creating a set of rules and protocols for resolving disputes. These rules must be designed to address everything from personal conflicts to disagreements over resource allocation. Having established systems in place helps settlers understand how conflicts will be addressed fairly and efficiently. Given Mars's unique environment, communication and social dynamics can also be a source of tension. The psychological effects of isolation and the harsh environment may lead to stress and interpersonal issues. Support systems, including mental health resources and conflict resolution training, will be essential for maintaining the well-being of settlers. Resource scarcity will be a major factor in potential conflicts, especially in the early stages of colonization. Decisions regarding the distribution of water, food, and energy will inevitably spark disagreements. Clear policies and transparent decision-making will help manage these resources equitably, reducing tensions related to unequal access. Cultural and social differences among settlers from diverse backgrounds can also lead to friction. As the colony grows, people will bring different values, customs, and priorities. Encouraging respect, inclusion, and dialogue between different groups will help mitigate potential conflicts and foster a sense of unity. Emergencies or unexpected events such as equipment failures or natural disasters can also trigger conflict as resources become even more limited. Preparation for such crises, including contingency plans and emergency protocols, will ensure that conflicts arising during stressful situations are managed quickly and fairly. The role of governance in conflict management is crucial. Effective leadership will need to strike a balance between ensuring order and allowing individual freedoms. Strong, transparent leadership will inspire trust and confidence among settlers, helping to prevent power struggles and authoritarianism from emerging. Technology will also play a role in conflict management on Mars. Surveillance systems, communication networks, and even AI-driven tools could assist in identifying potential issues before they escalate. These systems must be used with care to respect privacy while maintaining security. Physical space will be another important consideration. Overcrowding, restricted mobility, or lack of privacy can heighten tension among settlers. Urban planning, including the design of personal spaces and communal areas, will need to ensure that each individual's need for space and comfort is considered. Legal frameworks will also help settle conflicts over ownership, labor, and intellectual property. As Martian colonies develop, questions about land rights and resource ownership will become increasingly important. Establishing a clear legal system will ensure that these issues are resolved peacefully and fairly. The establishment of intercolony relationships could also lead to conflicts. Disputes between different settlements over resources, territorial claims, or political ideologies are likely to arise. Diplomacy and collaboration between colonies will be necessary to prevent these conflicts from escalating into larger, more dangerous situations. Education in conflict resolution and cooperation will be essential from the outset. Settlers must be prepared to handle disagreements constructively, with an emphasis on communication and compromise. By fostering a culture of respect and understanding, conflicts can be minimized and the colony's development can proceed smoothly. The timeline for full terraforming on Mars is an immense challenge that spans centuries. The process of transforming the Martian environment into a place where humans can live sustainably is not something that can be accomplished quickly. Each step requires careful planning, extensive research, and the gradual accumulation of technological and ecological advancements. The first phase of terraforming will focus on warming the planet and thickening the atmosphere, a task that could take decades. Releasing greenhouse gases, such as carbon dioxide, and using technology to trap heat will gradually increase the surface temperature. During this time, scientific teams will closely monitor the planet's response to ensure that the changes are sustainable. Building a breathable atmosphere rich in oxygen and nitrogen will likely take centuries. While early efforts may focus on introducing plants and microbes to produce oxygen, the process will be slow and gradual. The development of advanced bioengineering techniques will likely be necessary to speed up the oxygenation process. In addition to atmospheric changes, creating a stable water cycle on Mars will be essential. Melting the polar ice caps and establishing permanent water sources will take time. As the atmosphere thickens and temperatures rise, more water will become available for both human and ecological needs. Agricultural systems will need to evolve alongside the changing environment. In the early stages, food production will rely heavily on closed-loop systems such as hydroponics. Over time, as the soil becomes more hospitable, open-air agriculture will become feasible, further supporting the growing Martian population. The establishment of permanent ecosystems will take time as well. Introducing plants and animals will require careful management to ensure they can thrive in the evolving environment. These ecosystems will need to be self-sustaining, with minimal intervention from Earth to ensure long-term stability. The development of infrastructure, including habitats, energy systems and transportation networks, will proceed alongside terraforming efforts. Early habitats will be domed and heavily reliant on Earth for support. Over the centuries, as the environment becomes more hospitable, these structures will evolve into more permanent buildings, integrated with the natural landscape. Reaching a point where Mars can support human life without the need for artificial environments will take hundreds of years. This will depend on the success of terraforming efforts, such as the creation of breathable air, stable temperatures, and water availability. Gradually, humans will be able to transition from protected habitats to open environments. Technological advancements will accelerate the terraforming process, with each new development adding years to the timeline. Innovations in energy production, resource extraction, and environmental control will improve efficiency and reduce the time required to make Mars habitable. These breakthroughs will be key to moving the timeline forward. As the process continues, the pace of change will gradually increase. Once the basic systems for sustaining life are in place, the final stages of terraforming will focus on fine-tuning the environment. This could include stabilizing the weather, optimizing resource distribution, and ensuring that ecosystems are resilient. Intergenerational efforts will be required, with each generation building on the work of those before them. Colonists living on Mars in the early stages of terraforming will not see the final result, but their efforts will lay the foundation for future generations. This long-term commitment is necessary to achieve the ultimate goal of a fully transformed Martian environment. The full terraforming of Mars will be a milestone in human history, but it's a process that will require patience, persistence, and collaboration. While the exact timeline is uncertain, each step brings humanity closer to a world where life can flourish. Through continuous advancements in science and technology, Mars can one day become a thriving, sustainable planet. A terraformed Mars could resemble Earth in many ways, with a breathable atmosphere, vibrant landscapes, and functioning ecosystems. The sky would no longer be the dull red it is today, but rather a more familiar blue thanks to the presence of oxygen and nitrogen in the air. With thickened clouds, seasonal weather patterns, and a water cycle, Mars could eventually support life as we know it. The surface of Mars would be covered in vast expanses of green as plants and vegetation begin to flourish. Lush forests, fields of crops, and wetlands could dominate the landscape, supported by fertile soil that has been enriched through centuries of effort. These plant life forms would not only beautify the planet, but also provide oxygen, food, and a stable environment. Rivers and lakes would carve through the landscape, creating diverse ecosystems that support both plant and animal life. Water could flow freely through the planet, giving rise to wetland areas, beaches, and coastlines. These bodies of water would also play a crucial role in regulating the climate and providing resources for agriculture and human settlement. The Martian poles, once frozen wastelands, would be transformed into areas of thriving ice sheets and open waters. Melting the polar ice caps would create large bodies of water, forming seasonal oceans and expanding the habitable regions of Mars. The polar regions could also host new species of plants and animals adapted to the colder conditions. Mountain ranges, plains, and valleys could be sculpted by water, creating dramatic terrains with rivers running through them. Similar to Earth's landscapes, Mars would feature varying climates and ecosystems, from tropical forests to temperate zones. These differences in climate would add to the diversity of the planet, creating rich biomes that foster life. Wildlife, including birds, insects, and small mammals, could begin to populate Mars. Over time, more complex species could be introduced as the ecosystems stabilize and food chains develop. These species would fill various ecological niches, contributing to the planet's biodiversity and supporting human agriculture. Cities and settlements would be integrated into the Martian landscape, seamlessly blending with the natural environment. Homes and infrastructure could be built from local materials, reducing the need for resources from Earth. Green spaces and agricultural areas would be included in urban planning, ensuring that settlements remain self-sustaining. Oceans and seas, once a distant dream, could cover parts of Mars' surface. These large bodies of water would not only provide essential resources, but also help regulate the planet's climate. Coastal regions could become popular areas for human settlement, offering a connection to the planet's oceans. The atmosphere would protect Mars from harmful solar radiation, making outdoor life possible without the need for constant shelter. With a stable, breathable atmosphere, humans could explore the Martian surface freely. Weather patterns could bring rain and storms, further supporting ecosystems and agriculture. Mars' gravity would be close enough to Earth's to support human life in the long term, with settlers able to live and work without constant strain. This similarity in gravity would make long-term habitation easier and healthier. Settlements would be able to expand and thrive, with the potential for growing populations. Renewable energy sources, including solar farms and wind turbines, would power cities and settlements. The Martian surface would be covered in large-scale energy generation systems, tapping into the planet's resources. These sustainable energy practices would ensure that colonies remain operational and environmentally friendly. The atmosphere's oxygen levels would allow humans to breathe freely outdoors without protective gear. With no need for constant pressure domes or habitats, the Martian surface would be transformed into a more inviting and livable space. Mars would no longer be a cold, barren wasteland, but a thriving, Earth-like planet. Terraforming Mars has the potential to radically change the future of humanity. Establishing a self-sustaining colony on another planet could solve overpopulation issues, provide new resources, and create opportunities for exploration and innovation. It would be a bold step toward becoming a multiplanetary species, securing humanity's long-term survival. The ability to live on Mars would push the boundaries of science and technology, encouraging advancements in fields like bioengineering, energy production, and robotics. These breakthroughs would not only benefit Martian colonists, but could also be applied to solve problems on Earth, improving life for billions of people. The innovations developed for terraforming could be transformative. Building a thriving colony on Mars would require international collaboration on an unprecedented scale. Governments, corporations, and scientific organizations from around the world would need to work together to pool resources, share knowledge, and solve complex challenges. This collaboration could foster global unity and inspire new forms of cooperation beyond Earth's borders. As humanity expands to other planets, the ethical considerations of colonization will become even more important. Decisions on how to manage resources, the rights of settlers, and the treatment of any potential life on Mars will shape the future of interplanetary governance. Ethical frameworks must evolve alongside technological advancements to ensure that humanity acts responsibly. Living on Mars would also redefine the way we view Earth. As settlers on Mars look back at their home planet, they will likely develop a deeper appreciation for its fragility and uniqueness. This perspective shift could inspire new efforts to preserve and protect Earth, emphasizing the importance of sustainability and environmental stewardship. The creation of a permanent settlement on Mars would also offer new frontiers for human culture. A Martian society would develop its own identity, influenced by the challenges of living on a new world. New forms of art, communication, and social organization could emerge, reflecting the unique experience of living on a different planet. Mars could become a new hub for human civilization, offering opportunities for those who seek adventure, scientific discovery, or escape from challenges on Earth. A Martian colony would provide a diverse, dynamic environment where new ideas and cultures could flourish. This expansion could create a vibrant society with a unique mix of Earth-born traditions and new innovations. The terraforming of Mars could lead to a new era of space exploration. As humans learn to thrive on another planet, they will gain the skills and knowledge necessary to explore the rest of the solar system. Mars could become a stepping stone for future missions to the outer planets and beyond, further expanding humanity's reach into the cosmos. The ability to survive on Mars would also have profound implications for space travel. Advancements in transportation, life support systems, and radiation protection could pave the way for long-duration missions to other planets or even other star systems. With Mars as a base, humanity could explore deeper into space than ever before. Mars colonization would also create new economic opportunities. As industries grow on Mars, from mining to agriculture to energy production, new markets and industries would emerge. The economic activities on Mars could generate wealth and provide employment, creating a thriving economy that extends beyond Earth. Over time, the people of Mars may develop a distinct culture and identity, shaped by the challenges and opportunities of living on the red planet. This could lead to a new social dynamic, with Martians becoming a separate yet interconnected branch of humanity. The interplay between Earth and Mars would shape both societies in unexpected ways. Terraforming Mars is more than just a scientific or technological endeavor. It's a transformative opportunity for humanity. It offers a chance to expand our horizons, solve pressing problems, and create a future where humanity thrives on multiple worlds. The impact of this endeavor will resonate for generations, shaping the course of human history for centuries to come. As Mars becomes increasingly habitable, the next logical step for humanity is to look beyond the red planet. Expanding our reach to other celestial bodies offers opportunities for further exploration, resource gathering, and even the potential for new homes. The skills developed on Mars, from space travel to habitat construction, will serve as a foundation for future ventures. The moons of Jupiter, such as Europa, could become key targets for exploration. Their potential for subsurface oceans could support life and offer resources that are invaluable for further space colonization. Missions to these moons would require advanced technology and long-duration space travel, setting the stage for humanity's next great challenge. The asteroid belt is another area ripe for exploration. With vast resources, including metals and water, asteroids offer the potential for mining operations that could support space infrastructure on a much larger scale. Establishing mining colonies in the belt would provide materials for future colonies and fuel for interplanetary travel. The outer planets, including Uranus and Neptune, may also be targets for exploration and potential settlement. While they present significant challenges due to their extreme distances and hostile environments, advancements in propulsion and energy generation could make these missions feasible. The outer planets hold mysteries that could drive scientific discovery and innovation. Interstellar exploration might be the ultimate goal for humanity's expansion beyond Mars. With the development of faster propulsion systems, distant star systems could eventually become reachable. Exploring planets around other stars opens up the possibility of finding life beyond our solar system and learning more about the universe. To make expansion beyond Mars feasible, humanity will need to develop advanced propulsion systems. Faster spacecraft, capable of traveling at a significant fraction of the speed of light, are critical to exploring distant planets and stars. These advancements will revolutionize space travel and open up new frontiers for humanity. Space stations in orbit around Earth or Mars could serve as hubs for interplanetary travel, offering refueling, research, and manufacturing facilities. These stations will act as critical nodes in a growing network of human presence in space, allowing for easier and more frequent travel to and from distant locations in the solar system. Space agriculture will need to be perfected for long-term missions to distant destinations. Developing closed-loop farming systems that can function without constant input from Earth is essential for sustaining long-duration space missions. These systems could also support colonies in the asteroid belt or on the moons of Jupiter and Saturn. Artificial intelligence and robotics will play a significant role in the expansion of humanity's presence in space. Autonomous robots will be crucial for construction, mining, and even scientific research in environments that are inhospitable to humans. These technologies will extend humanity's reach and ensure that space colonization progresses smoothly. As humanity continues to spread throughout the solar system, the need for sustainable energy sources will grow. Solar power, nuclear fusion, and potentially even antimatter will be explored as viable energy sources for long-duration missions. Harnessing these energy sources efficiently is crucial for powering habitats, spacecraft, and other infrastructure. Establishing a presence beyond Mars will also involve political and legal considerations. Interplanetary treaties, governing bodies, and regulations for resource extraction will need to be created to ensure that space colonization is peaceful and cooperative. These frameworks will guide the ethical use of resources and the governance of space settlements. The ultimate goal of expanding beyond Mars is to ensure the survival and thriving of humanity across multiple planets and systems. By establishing colonies and developing technologies to support life in space, humanity will ensure its place in the cosmos for generations to come. The steps taken today will shape the future of human civilization in the universe. Creating a new world like Mars raises profound philosophical questions about humanity's role in the universe. By transforming a barren planet into a thriving ecosystem, we are not just altering the environment, but also redefining what it means to be human. This endeavor challenges us to consider our responsibilities toward the environment, life, and future generations. Now, the question of whether it is ethical to terraform a planet is one of the most pressing concerns. Are we justified in altering a world that has evolved on its own terms, even if it appears lifeless? As we shape Mars into a more hospitable environment, we must also reflect on the potential consequences for any future life forms that might exist or that we might create. Our ability to change the environment to suit human needs introduces questions about power and control. Who decides the direction of this transformation? What moral framework will govern the decisions made? And how will we ensure that the benefits of Mars' transformation are shared equitably among all its inhabitants? The colonization of Mars also invites us to reconsider our relationship with Earth. As we expand our presence into the cosmos, we must ask what it means to be stewards of our home planet. The lessons we learn from Mars in terms of sustainability, resource management, and resilience could reshape how we interact with Earth and its ecosystems. As humans create a new world, we may also grapple with existential questions about the nature of life and civilization. Will Mars become a mirror of Earth, repeating the same mistakes, or can it become a second chance to build a better world? These reflections will guide how we approach governance, society, and technology on a new planet. The creation of a new world also raises questions about identity and culture. As humans adapt to life on Mars, new identities and ways of life will emerge. Over time, Martian settlers may develop distinct cultural practices, influenced by their environment and challenges, leading to the formation of a society that differs from Earth's. One of the philosophical challenges is considering the implications for future generations born on Mars. What rights will they have as the inheritors of a world that has been deliberately shaped? Will they feel a connection to Earth, or will they see Mars as their true home, with its own unique identity and history? The act of terraforming and colonizing Mars also invites a broader philosophical inquiry into the nature of progress. What does it mean for humanity to be progressing? And what is the ultimate goal of this journey? Is it simply survival, or is it about achieving something more meaningful and enduring, creating a civilization that can exist independently of Earth? The potential for life on Mars, whether it be through terraforming or through the creation of new life forms, raises deep questions about the nature of life itself. If we succeed in creating life on Mars, will it have intrinsic value, or will it simply be a tool for human survival? These questions touch on the very essence of what it means to create, nurture, and sustain life. The concept of home will also shift as humanity establishes a permanent presence on Mars. What does it mean to call a place home when that place is so far removed from Earth, both physically and emotionally? This emotional and philosophical connection to Mars will influence how settlers view their world, their purpose, and their legacy. There is also the question of cosmic significance. What does it mean for humanity to take its first steps in becoming a multi-planetary species? Are we simply fulfilling a natural urge to explore, or is there a deeper existential need to become a part of the cosmos, to ensure that our species is not bound to just one world? Finally, the philosophical implications of creating a new world force us to confront the broader meaning of our existence. Are we shaping Mars to reflect our own values, or are we truly adapting to a new world, one that might challenge us in ways we cannot yet foresee? This tension between creation and adaptation will be one of the most defining aspects of humanity's future on Mars. In this video, we've explored the fascinating topic of terraforming Mars and its potential to reshape humanity's future. We delved into the various stages of transforming the Martian environment, from warming the planet and creating a breathable atmosphere to developing sustainable ecosystems. Through each phase, we saw the monumental effort required to make Mars a viable home for future generations. We also examined the role of international space agencies and private companies, highlighting how collaboration and innovation will be critical in overcoming the challenges of Mars colonization. Whether it's the development of new technologies like reusable spacecraft, or creating laws and ethical frameworks for a new society, the combined efforts of governments, corporations, and scientists will play a huge part in making Mars a reality. As we considered the technological advancements needed to terraform Mars, we looked at the importance of energy sources, transportation systems, and 3D printing for infrastructure. These technologies will allow us to harness the resources of Mars, build sustainable cities, and create the systems necessary for human life to flourish on the planet. We also explored the philosophical implications of creating a new world, from the ethical considerations to the existential questions about humanity's role in the universe. The timeline for full terraforming of Mars is ambitious, spanning centuries, but the possibilities are endless. With each technological breakthrough and environmental success, we get one step closer to the vision of a thriving Martian colony. And as humanity continues to reach beyond Mars, the lessons learned from this endeavor will shape the future of space exploration for generations to come. If you enjoyed learning about the complex and exciting journey of terraforming Mars, be sure to like and subscribe to our channel for more in-depth videos on space exploration and the future of humanity. By subscribing, you'll be the first to know when we release new content that delves into other thrilling topics in science, technology, and the cosmos. We invite you to check out the rest of our videos on the channel, where we cover a wide range of subjects related to space exploration, sustainable technologies, and the incredible potential of human innovation. Whether you're a space enthusiast or just curious about the future of our planet and beyond, there's something here for everyone. By subscribing and engaging with our content, you'll become part of a growing community of explorers and thinkers. You'll get access to exclusive content, updates, and discussions on the cutting edge of science and exploration. Join the conversation, share your thoughts, and stay connected with us as we continue to explore the possibilities of humanity's future in space. We want to hear from you. What do you think about the terraforming of Mars? Do you believe humanity should take on this ambitious project, or do you have concerns about its impact on the Martian environment? Share your thoughts in the comments below. We love hearing from our viewers and engaging in thoughtful discussions. Thank you for watching this video, and if you're as excited about the future of space as we are, make sure to explore our other content. From the latest space missions to theories on extraterrestrial life, we're here to provide you with the knowledge and inspiration to expand your horizons. Remember, every like, share, and comment helps us continue producing the content you love. So don't forget to show your support by hitting the thumbs up button and subscribing to our channel. Together, we'll explore the unknown and unlock the mysteries of the universe.